Humans may be the only animals who built cities, wrote philosophy, and mapped the stars, yet many of us are quietly hurt by the simple act of carrying our own bodies upright. Wolves run, cats stretch, horses stand, and even apes rarely live with the long, stubborn back pain that follows humans across decades. What makes this so strange is that the human spine was not ruined by failure, but shaped by a survival advantage that came with a hidden cost. Why humans are the only animals with back pain? For most of the history of life with a backbone, the spine was never meant to stand upright. It stretched horizontally from head to tail, forming a flexible bridge that allowed bodies to move across the ground, through water, and over uneven landscapes. Fish carried this structure through ancient oceans. Reptiles carried it across the first dry continents. Mammals inherited the same basic design and adapted it for running, climbing, and leaping. In almost every case, the spine worked like a suspended beam, supported by 4 limbs that distributed the weight of the body across a broad base. Gravity pressed downward, but it was shared across the entire frame of the animal. The spine did not carry the full burden alone. When early humans eventually appeared on Earth, they inherited this same ancient structure. The bones, the discs between them, and the delicate nerves passing through the center were all part of a system that had already been tested for hundreds of millions of years in creatures that moved on 4 limbs. Yet somewhere along the long path of human ancestry, a quiet change began to reshape how this structure worked. The ancestors of humans gradually shifted their posture. Instead of leaning forward with the spine parallel to the ground, their bodies began to rise. The head balanced above the shoulders, the torso lifted. The spine, which had once acted like a bridge between limbs, slowly turned into a vertical column supporting the weight of the entire upper body. From a distance, the change might appear simple, 2 legs instead of 4. But within the body, the mechanical consequences were profound. Gravity now pressed directly downward along the spine. Every vertebra stacked upon the next like stones in a narrow tower. The soft discs between them absorbed pressure with each step, each bend, each moment spent standing. This transformation did not happen overnight. Fossil evidence from early members of the human lineage suggests that the shift toward upright walking unfolded gradually over millions of years. Species such as Australopithecus already showed signs of habitual bipedal movement roughly 3 to 4 million years ago. Their pelvis, leg bones, and spinal curvature indicate bodies that were learning to balance upright while still retaining some traits suited for climbing. These early humans lived in environments where moving efficiently across open landscapes mattered for survival. Standing upright allowed the hands to carry food or tools. It raised the eyes higher above grasses and shrubs, making it easier to detect predators or distant resources. Over many generations, natural selection favored bodies that could maintain this posture with increasing stability. The spine slowly developed gentle curves that helped distribute weight more effectively. Instead of remaining straight like the spine of most quadrupeds, the human spine formed a subtle shape. These curves acted like springs, softening the impact of each step while keeping the head balanced over the hips. Even with these adjustments, the structure remained an adaptation built upon a far older blueprint. The vertebrae themselves still resembled those of other mammals. The discs between them still functioned as cushions designed originally for a body carried horizontally. In evolutionary terms, the human spine was not built from the ground up for upright life. It was modified from an older system that had evolved for a different orientation to gravity. This distinction matters when considering a quiet puzzle of modern life. Many animals run, jump, twist, and carry heavy loads without developing the persistent back pain that affects large numbers of humans. Meanwhile, human societies, despite medicine, technology, and comfortable living conditions, report widespread discomfort in the lower back and neck. The origin of this difference may not lie in weakness or failure, but in the history embedded within the bones themselves. The human spine is both ancient and newly repurposed at the same time. It carries the memory of a horizontal past while supporting a vertical present. Understanding how this unusual combination came to exist begins with recognizing that the human body did not start from a blank page. It began with structures shaped by distant ancestors who never stood the way we do today. Long before the first humans walked across open plains, the blueprint of the spine had already existed for an immense stretch of time. The earliest vertebrate ancestors lived in ancient seas more than 500 million years ago. In those environments, the body did not rise above gravity but moved within water, where buoyancy reduced the burden placed on skeletal structures. The primitive backbone functioned as a flexible rod running along the length of the body, helping muscles generate smooth side-to-side motion. This early structure, sometimes called a notochord, eventually evolved into the segmented vertebrae seen in later animals. When vertebrates began to move onto land hundreds of millions of years later, the same basic design remained. Amphibians and reptiles carried their bodies across the ground with the spine positioned horizontally between four limbs. Each limb absorbed part of the body's weight, while the spine mainly coordinated movement and flexibility. Mammals inherited this arrangement and refined it further. In animals such as wolves, horses, and deer, the spine functions as a dynamic beam suspended between the front and rear limbs. Muscles and ligaments support it from both directions, allowing the body to run with remarkable efficiency. During motion, the spine bends and straightens rhythmically, storing and releasing energy like a spring. This design spreads forces across the entire body rather than concentrating them in a single column. When gravity presses downward on a running animal, the load is divided among four limbs and distributed through powerful muscles along the back and abdomen. The vertebrae and the discs between them experience pressure, but the direction of that pressure differs from what occurs in the human body. Instead of compressing vertically through a stacked tower of bones, much of the force travels along the length of the spine, shared with surrounding tissues. This difference may seem subtle, yet it shapes how the structure endures stress across a lifetime. Observations of living mammals rarely reveal the kind of persistent lower back pain common among humans. Dogs and horses can develop spinal injuries, especially after trauma or extreme strain, but long-term degenerative pain that limits daily movement appears far less frequently. The reason is not that their spines are stronger in every way, rather, their bodies continue to use the design for which the spine originally evolved. Their posture preserves the ancient relationship between gravity, limb support, and spinal flexibility. In contrast, the human body gradually moved away from this arrangement. As human ancestors began to rely more on upright walking, the orientation of the spine changed relative to gravity. Instead of hanging between limbs, it began to function as the central pillar of the body. The head balanced above it, the chest and abdomen rested upon it, and the pelvis anchored it to the legs. Over time, the vertebrae near the lower back became larger and thicker, reflecting the increased load they were required to bear. Fossil evidence from early members of the human lineage shows that these changes did not erase the older design entirely. The vertebrae still resemble those of other mammals in many fundamental ways. The discs between them remain soft cushions designed to absorb movement and shock. Ligaments continue to hold the bones together while allowing flexibility. These elements reveal that the human spine is not an entirely new invention of evolution. Instead, it represents a careful modification of a structure far older than the human species itself. When the earliest humans stood upright on the African landscape several million years ago, they carried within their bodies the legacy of animals that had never walked that way. The spine that supported their posture had once served a different orientation to the world. It had evolved under conditions where the body extended horizontally, supported by four limbs moving across the ground. As generations passed, the spine adapted gradually to its new role, developing curves and strengthened vertebrae to help manage the shifting forces of gravity. Yet the underlying architecture remained connected to its deep evolutionary past. Recognizing this long history helps explain why the human spine occupies such a delicate position between stability and strain. It functions both as an ancient structure and as a relatively recent adaptation to upright life. This tension between old design and new demands forms the quiet background behind many of the physical experiences humans now consider ordinary. When a structure that evolved for one environment begins to operate in another, the change rarely appears dramatic at first. It unfolds slowly, through small adjustments that accumulate across generations. The human spine followed this pattern. Early human ancestors did not suddenly transform from four-limbed movement into perfectly balanced upright walkers. Their bodies carried traces of both worlds. Fossils from species living several million years ago show skeletons that still climb trees while also walking on the ground. Their arms remained relatively long, their fingers curved for gripping branches, and their shoulders retain the mobility of arboreal primates. Yet the pelvis and lower limbs already reveal a shift toward habitual upright movement. In this transition, the spine became the central structure that allowed the body to balance between these two modes of life. One of the most important changes involved the gradual formation of spinal curvature. Most quadrupedal mammals have a spine that remains relatively straight when viewed from the side. Humans, however, developed a sequence of curves that together create the familiar shaped profile. The cervical curve near the neck tilts the head slightly backward so that the eyes face forward rather than toward the ground. The thoracic region curves gently in the opposite direction, forming the rounded section behind the chest. Below this, the lumbar curve bends forward again, positioning the upper body directly above the hips. These curves did not appear as decorative features. They emerged as mechanical solutions that help distribute the vertical forces acting on an upright body. Each curve functions like a spring that absorbs movement and reduces the shock transmitted from the ground during walking. When a person takes a step, the body rises and falls slightly with each stride. The curved spine softens these oscillations, preventing them from traveling unfiltered to the skull and brain. In this sense, the human spine demonstrates remarkable adaptability. It reshaped itself to support a posture rarely seen among mammals. However, this adaptation did not erase the structural limitations inherited from the past. The vertebrae of the lower back, particularly the lumbar vertebrae, became larger than those above them because they carried increasing amounts of weight. These bones now support not only the trunk, but also the forces produced by lifting, bending, and twisting. Between each vertebra sits a disc made of tough outer fibers surrounding a softer inner core. These discs compress slightly under pressure, acting as cushions that allow the spine to remain flexible. Over decades of use, however, the repeated compression and movement can slowly alter the condition of these discs. This gradual wear does not necessarily indicate damage or weakness. It reflects the long process of a structure working continuously under gravity. In most animals, the spine shares its workload with four limbs and powerful trunk muscles that help suspend the body horizontally. Humans, by contrast, rely on a vertical stack of vertebrae to maintain balance throughout standing and walking. Muscles in the back and abdomen assist in stabilizing this column, but the fundamental orientation remains different from that of other mammals. Archaeological evidence from ancient human skeletons shows that signs of spinal stress appeared long before modern life introduced chairs, desks, or sedentary work. Some prehistoric skeletons reveal vertebral changes associated with heavy physical activity, carrying loads, or repetitive movement. These findings suggest that the challenge of maintaining an upright spine has existed throughout much of human history. Yet the presence of such changes also indicates something else. Despite these stresses, the spine allowed humans to travel long distances, gather food across varied landscapes, and adapt to many environments. The same structure that sometimes produces discomfort also made an extraordinary way of life possible. The human body therefore carries an unusual balance between resilience and vulnerability. The spine supports the posture that freed the hands for tools, enabled endurance walking, and shaped the course of human survival. At the same time, it remains a structure whose origins lie in a very different orientation to gravity. This dual history is written quietly into the bones themselves, forming the background to a question that becomes clearer only when the deep past of the body is considered carefully. If the human spine is to be understood clearly, it helps to step far beyond the history of our own species and look into a deeper chapter of life on Earth. Long before mammals appeared, long before the first primates moved through forests, the basic architecture of the spine had already taken shape in ancient vertebrates. These early animals lived in oceans that covered much of the planet hundreds of millions of years ago. Their bodies were simple compared with those of later creatures, yet the core idea of a flexible central support had already emerged. Running through the length of their bodies was a structure known as the notochord, a rod made of specialized cells that provided stability while still allowing movement. Muscles attached along its sides could contract in waves, bending the body left and right to push through water. Over time, evolution transformed this rod into a series of segmented bones called vertebrae. Instead of a single, flexible column, the spine became a chain of individual pieces stacked together. Between these pieces formed soft tissues that allowed slight motion while protecting the delicate spinal cord running through the center. This arrangement proved remarkably effective. It combined stability with flexibility, allowing animals to twist, turn, and respond quickly to their surroundings. When vertebrates eventually moved from water onto land roughly 400 million years ago, the same spinal blueprint remained in place. The transition from water to land brought new challenges. In water, buoyancy supported much of the body's weight. On land, gravity pressed downward continuously. Early amphibians and reptiles solved this problem not by redesigning the spine completely, but by spreading the body's weight across 4 limbs. The spine remained horizontal, connecting the head to the tail while the limbs carried the load. Muscles along the sides of the body stabilized the structure, and the vertebrae allowed enough flexibility for crawling and walking across uneven ground. As mammals later evolved from reptilian ancestors, the spine continued to follow this same basic pattern. What changed were the details. Mammalian vertebrae became more specialized, dividing into regions that supported different functions. The neck allowed the head to move independently. The thoracic region anchored the ribs and protected the lungs and heart. The lower back provided strength and flexibility for locomotion. These distinctions gave mammals greater control over movement and posture, yet the orientation of the spine remained horizontal. In running mammals such as wolves or antelope, the spine acts as a powerful spring during motion. When the animal gallops, the back flexes and extends rhythmically, increasing the length of each stride. Muscles and tendons store energy as the body compresses, then release it as the animal pushes forward. The spine, therefore, participates actively in locomotion rather than merely holding the body upright. Even large animals, such as horses, rely on this principle. Their spines distribute forces along the length of the body, supported by strong ligaments and the coordinated movement of 4 limbs. Through all these variations, the fundamental idea remains constant. The vertebrate spine evolved as a horizontal support system designed to coordinate movement across a body carried by multiple limbs. This deep evolutionary background explains why the same structure appears across a wide variety of animals, from fish to mammals. The differences between species arise mostly from how this ancient design is modified rather than replaced. When the first human ancestors began to move differently across the African landscape, they did not abandon this inherited blueprint. The vertebrae, discs, ligaments, and muscles that form the spine were already part of a system shaped by hundreds of millions of years of evolution. What changed was the way the body interacted with gravity. Instead of stretching forward between limbs, the spine gradually began to support the body vertically. The transformation did not erase the earlier design, but layered a new function upon it. Understanding this long history reveals that the human spine is not a structure invented specifically for upright life. It is an ancient framework adapted to a new role, carrying within it the memory of environments and movements far older than humanity itself. As vertebrates diversified across the planet, the spine gradually developed a pattern that still appears in nearly every mammal alive today. Instead of functioning as a single uniform rod, the backbone became organized into regions, each with a slightly different role. This regional design allowed the body to balance flexibility and strength while moving through complex environments. The neck, or cervical region, evolved to support the head while permitting a wide range of motion. In many mammals, the head must turn quickly to detect predators or prey, and the cervical vertebrae allow this movement without disturbing the rest of the body. Below the neck lies the thoracic region, where vertebrae anchor the ribs that surround the lungs and heart. These bones create a protective cage, while still allowing the chest to expand and contract with breathing. Further down, the body sits the lumbar region, a section that plays a crucial role in transferring forces between the front and rear limbs during movement. Finally, the sacral vertebrae connect the spine to the pelvis, forming the structural link that stabilizes the body as it moves across the ground. In quadrupedal mammals, this entire system operates within a horizontal framework. The spine stretches between the shoulders and hips, suspended by muscles and ligaments that act like cables supporting a bridge. When the animal walks or runs, each limb strikes the ground in sequence, and the forces generated by those impacts travel through the limbs before reaching the spine. The backbone participates in movement, but it rarely acts as the primary column carrying the entire body's weight. Instead, the load spreads outward across 4 limbs and through the muscular structures of the torso. This arrangement provides a remarkable balance between mobility and stability. A running animal can bend its spine to lengthen its stride while the limbs absorb much of the impact created by contact with the ground. The discs between the vertebrae compress and rebound, distributing pressure gradually rather than concentrating it in one location. Over millions of years, this design proved so effective that it remained largely unchanged across many lineages of mammals. Even animals with very different lifestyles still rely on the same general framework. A cat stalking quietly through grass, a horse galloping across open plains, and a chimpanzee climbing through branches all carry variations of the same spinal architecture. Each species modifies the length, shape, or flexibility of particular vertebrae, yet the orientation of the spine remains consistent. Gravity pulls downward on the body, but the weight is shared between the limbs and the supporting muscles surrounding the spine. This pattern also appears in our closest living relatives among the primates. Chimpanzees and gorillas possess vertebrae arranged in a way that resembles the human spine in many respects. However, their posture typically keeps the trunk angled forward rather than balanced directly above the hips. When these animals move across the ground, they distribute weight through their arms and legs simultaneously. Even when standing briefly on 2 feet, their bodies usually lean forward, maintaining a relationship with gravity that differs from the upright stance of humans. Because of this orientation, the forces acting on their vertebrae follow directions similar to those experienced by other quadrupedal mammals. The spine functions primarily as a flexible connector coordinating movement rather than as a vertical pillar supporting the entire upper body. The importance of this distinction becomes clearer when examining how evolutionary history shaped the human skeleton. The ancestors of humans inherited a spine already divided into specialized regions. Each evolved for life in a horizontal posture supported by multiple limbs. The vertebrae, discs, and ligaments that form this system were not newly invented for upright walking. They were adapted gradually from a framework designed for a different relationship between body and gravity. Over time, this inherited architecture would face new mechanical demands as human ancestors began to stand and walk with increasing frequency on 2 legs. Within this long evolutionary history, one feature of the spine remained especially important: the way its individual pieces share and redirect force. Each vertebra is shaped not only to support weight but also to guide motion in controlled directions. The bones are stacked together with small joints at their back edges, while soft discs sit between them like cushions. These discs are made of layers of strong fibers surrounding a softer interior that can compress and shift slightly under pressure. When a vertebrate body moves, these discs allow the spine to bend smoothly without damaging the delicate spinal cord that runs through the center of the vertebrae. In animals whose bodies remain horizontal, this system distributes movement across many segments rather than concentrating it in a single place. A running mammal rarely bends at one specific vertebra. Instead, the entire spine participates in a coordinated wave of motion that travels from shoulders to hips. Muscles along the back guide this motion, tightening and relaxing in patterns that keep the body balanced. The result is a structure that is both flexible and resilient. Forces created by running, jumping, or landing are absorbed gradually along the length of the back. No single vertebra must carry the full burden of the body alone. Over time, this arrangement proved remarkably durable. Mammals that spend their lives moving across rugged landscapes rarely show the kind of long-term spinal degeneration often reported in modern human populations. Injuries certainly occur, especially during falls or intense physical strain, yet the everyday act of movement rarely overwhelms the design of the spine. The relationship between limbs, muscles, and vertebrae spreads stress broadly across the body. Even when animals grow older, they often remain capable of walking, climbing, or running without the persistent lower back pain that has become familiar to many humans. This difference does not arise from a simple matter of strength. Many animals are physically stronger than humans relative to their body size, yet strength alone does not explain the stability of their backs. The deeper explanation lies in the way their bodies continue to use the spine according to the orientation for which it evolved. The horizontal arrangement allows gravity to act across the body in a way that is balanced by 4 supporting limbs. The spine remains part of a wider mechanical system rather than functioning as the central pillar of posture. The muscles of the abdomen and back form a supportive sling beneath the torso, while the limbs absorb the repeated impacts of movement against the ground. When examining this system from an evolutionary perspective, it becomes clear that the spine was never originally designed to act as a vertical tower of stacked bones. Its components developed in an environment where the body extended forward, supported at several points along its length. Each vertebra participated in a chain of motion rather than standing beneath the entire weight of the trunk and head. This background becomes especially important when considering the later path of human evolution. When early members of the human lineage began to adopt more upright forms of movement, they carried with them this deeply rooted design. The bones, discs, and ligaments that formed the spine had already been shaped by hundreds of millions of years of life in bodies oriented horizontally. The shift toward upright walking did not replace that architecture. Instead, it gradually transformed how the existing structure interacted with gravity. Vertebrae that once shared forces across a horizontal body would begin to stack vertically above the pelvis. Discs that once cushioned sideways bending would increasingly absorb downward compression. Muscles that once balanced the body between four limbs would take on new roles, stabilizing a tall column rising above the hips. In evolutionary terms, this change represents a modification layered upon a far older foundation. The spine of a human still carries the memory of its ancient function, even as it performs a new task. Recognizing this continuity allows the next step of the story to come into view, the moment when human ancestors began to stand and walk in a way that permanently altered the relationship between the spine and gravity. Several million years ago, somewhere within the landscapes of eastern and southern Africa, a subtle shift in posture began to reshape the bodies of a small group of primates. These ancestors did not yet resemble modern humans, and their lives still unfolded among trees, open woodland, and scattered grasslands. Yet something about the way they moved across the ground started to change. Instead of relying entirely on four limbs, they began to place increasing weight on their hind legs. At first, this shift may have been temporary, used while reaching for fruit, carrying food, or scanning the surroundings above tall grasses. Over many generations, however, the behavior became more frequent, and the skeleton slowly began to reflect it. Fossil discoveries from this period reveal creatures that walked in a way neither fully human nor entirely like other apes. Among the most famous examples is a species known as Australopithecus, which lived roughly 3 to 4 million years ago. Skeletons attributed to these early hominins show clear signs of habitual upright movement. The pelvis is shorter and broader than that of chimpanzees, allowing muscles to stabilize the body during bipedal walking. The thigh bone angles inward toward the knee, helping position the feet directly beneath the center of gravity. Even the footprints preserved in volcanic ash at Laetoli in present-day Tanzania suggest a stride remarkably similar to that of modern humans. Yet these same skeletons also retain features associated with life in trees. Their arms remain relatively long, their fingers curved, and their shoulders capable of movements suited for climbing. These details suggest that early human ancestors were still navigating both ground and branches, shifting gradually toward a new way of moving without abandoning the older one entirely. Within this changing body, the spine played a crucial role. In quadrupedal primates such as chimpanzees, the spine remains relatively straight and the trunk leans forward when the animal moves across the ground. Early hominins, however, began to develop a lower back capable of supporting a more vertical posture. Fossil vertebrae from these species indicate the presence of lumbar curvature, a forward bend that helps align the torso above the pelvis. This curvature allowed the upper body to balance more easily over the hips while walking on two legs. Instead of leaning forward with the arms supporting part of the weight, the torso could rise more directly above the legs. The change may seem modest when viewed from a distance, but its mechanical consequences were significant. Standing upright shifted the relationship between the spine and gravity. The weight of the head, chest, and abdomen now pressed downward through the vertebrae rather than hanging between the limbs. To manage this new orientation, the spine gradually formed the characteristic shaped pattern seen in modern humans. The lower back curved inward, the upper back curved outward, and the neck curved forward again to keep the head balanced above the body. These adjustments improved stability while walking, and freed the hands for carrying objects or manipulating tools. From an evolutionary perspective, bipedal walking offered several potential advantages. Moving on, two legs can conserve energy during long-distance travel, particularly across open terrain where food sources may be widely scattered. Upright posture also elevates the head, allowing individuals to look across grasses and detect predators or distant resources more easily. In addition, freeing the hands creates opportunities for carrying food, transporting infants, or using simple tools. Each of these possibilities may have contributed to the gradual spread of bipedal movement among early members of the human lineage, yet these benefits did not arrive without structural adjustments. The spine, inherited from ancestors that moved horizontally, now faced the challenge of supporting a body balanced vertically above the pelvis. Vertebrae in the lower back became larger to carry increased loads, while the discs between them absorbed repeated compression during walking and standing. Muscles along the back and abdomen took on new roles, stabilizing the upright torso. Over time, this combination of old design and new function created a spine capable of supporting the distinctive posture of humans. The transformation toward upright walking did not happen as a single moment in time. It unfolded across many generations as the bodies of early human ancestors gradually adjusted to a new balance with gravity. Fossil remains scattered across parts of Africa reveal how this transition progressed in small but meaningful steps. Bones of the pelvis, legs, and spine show a body slowly reorganizing itself around the ability to walk on two legs. These anatomical changes did not replace the older primate structure immediately. Instead, they reshaped it piece by piece, while preserving many elements inherited from earlier ancestors. One of the most revealing clues appears in the structure of the pelvis. In apes that move primarily on four limbs, the pelvis is relatively long and narrow. This arrangement supports muscles used for climbing and for moving with the trunk angled forward. Early members of the human lineage developed a pelvis that became shorter and broader. This shift changed the way certain muscles attached around the hips, allowing them to stabilize the body while standing on one leg during walking. Each step in bipedal movement briefly places the entire weight of the body over a single limb, requiring careful balance that quadrupedal animals rarely experience. The altered pelvis helped maintain this balance, preventing the torso from tipping sideways as the body moved forward. The legs also reveal important adjustments. The femur, or thigh bone, began to angle inward from the hip toward the knee. This inward angle brought the feet closer to the center of gravity beneath the body. Instead of spreading outward as they do in many quadrupedal animals, the legs aligned more directly under the torso. This alignment made walking more efficient by reducing the side-to-side swaying that would otherwise occur if the feet were placed too far apart. Each of these changes influenced the spine, which had to coordinate the movement of the upper body with the shifting base of support provided by the legs. Vertebrae from early hominin fossils suggest that the lower back contained several lumbar segments capable of forming a gentle curve. This curvature helped position the upper body above the pelvis rather than in front of it. The shift allowed the head to balance more easily while the body remained upright. In chimpanzees, by contrast, the lumbar region is shorter and less curved, reflecting a posture in which the trunk leans forward during movement. The difference between these arrangements illustrates how subtle modifications to the spine helped accommodate a new relationship between the body and gravity. Archaeological discoveries also provide indirect evidence of how these anatomical changes influenced everyday movement. The footprints preserved at Laetoli, formed roughly 3.6 million years ago when volcanic ash captured the steps of several individuals walking across a damp surface, reveal a pattern strikingly similar to that of modern human walking. The heel strikes the ground first, followed by a rolling motion through the foot toward the toes. This pattern suggests a stride adapted for efficient bipedal travel rather than the bent hip, bent knee posture sometimes used by apes when moving briefly on two legs. Even so, the early hominin skeleton retained traits suited for climbing. Long arms and curved fingers hint at time still spent among branches. This mixture of features suggests that upright walking developed within a flexible lifestyle rather than replacing earlier behaviors all at once. Within such bodies, the spine served as a central axis linking the head, trunk, and limbs. As walking became more frequent, the vertebrae experienced forces that differed from those acting on the spines of other primates. Instead of supporting a body leaning forward between arms and legs, the spine increasingly carried the vertical load of the torso. Muscles along the back worked continuously to stabilize this column while the pelvis and legs managed the shifting balance of each step. Over thousands of generations, natural selection favored individuals whose skeletal structures handled these demands more effectively. The result was a spine gradually reshaped to function within a body that had begun to move through the world in a distinctly human way. As the habit of upright walking became more common among early members of the human lineage, the body slowly reorganized itself around a new center of balance. Walking on two legs does not simply change the number of limbs touching the ground. It alters the entire relationship between gravity and the skeleton. In a quadrupedal body, the center of mass lies between 4 points of support. The spine stretches forward between shoulders and hips, while the limbs absorb and redistribute the weight of the body during movement. When early humans began to rely more consistently on two legs, that balance shifted dramatically. The entire upper body, head, chest, arms and organs now had to remain balanced above the pelvis while the legs moved beneath it. Within this arrangement, the spine became the structure responsible for keeping the torso upright. The vertebrae of the lower back gradually adapted to handle increasing pressure created by the vertical alignment of the body. Fossil evidence suggests that these vertebrae grew broader and stronger over time. Their shape allowed them to bear the weight transmitted from the upper body while still permitting enough flexibility for bending and twisting. The discs between these vertebrae also played an important role. Each disc acts as a cushion composed of strong outer layers surrounding a softer inner core. When a person walks, runs, or lifts objects, these discs compress slightly and then rebound, absorbing some of the forces produced by movement. In early hominins, this system helped soften the repeated impacts of footsteps traveling upward from the ground. Another crucial adjustment involved the arrangement of spinal curves. Earlier primates typically carry a relatively straight spine when viewed from the side. Humans, by contrast, developed a pattern of curves that allowed the body to remain balanced above the hips. The lower back bends gently forward, creating a lumbar curve that positions the upper body directly above the pelvis. Above this, the thoracic region curves slightly backward behind the chest, and the neck curves forward again to support the head. Together, these curves create the familiar shaped structure of the human spine. Rather than being a sign of weakness, these curves function as a mechanical system that spreads forces more evenly across the spine during movement. When the body rises and falls with each step, the curves act like springs that reduce the intensity of the forces traveling through the vertebrae. These adjustments allowed early humans to move efficiently across landscapes that often required long-distance travel. Evidence from archaeological sites suggests that members of the genus Homo eventually developed remarkable endurance for walking and running. Long legs, efficient strides, and upright posture made it possible to cover significant distances while searching for food or following migrating animals. In this environment, the spine played a central role in maintaining balance and absorbing the repeated shocks of locomotion. Yet even as the body adapted to upright movement, the spine continued to reflect its deeper evolutionary origins. The vertebrae remained part of a system first shaped in animals whose bodies extended horizontally across the ground. The discs between them retained structures designed to handle bending and flexing rather than constant vertical compression. Muscles along the back and abdomen helped stabilize the upright torso, but they could not entirely remove the mechanical demands placed on the vertebral column. Over many generations, natural selection favored bodies capable of managing these stresses while maintaining mobility. The resulting spine represents a compromise between ancient design and new function. It allows humans to stand, walk, and carry objects with remarkable versatility, yet it does so using a framework inherited from ancestors that never lived with gravity, pressing downward through a vertical column of bones. This quiet compromise forms part of the deeper story behind why the human spine behaves differently from the spines of most other animals. Standing upright gave early humans a new way of moving through the world, yet this posture also introduced a subtle mechanical challenge that few other animals experience. When the body rises onto two legs, gravity begins to act on the spine in a very different direction. Instead of being shared across 4 limbs and distributed along a horizontal structure, the weight of the head, chest, and arms now presses downward through a vertical column of vertebrae. Each bone rests upon the next, and the forces created by movement travel along this stacked arrangement toward the pelvis and legs. In a sense, the spine becomes both the central support of the body and the pathway through which gravity constantly moves. This arrangement works well enough for an upright species to walk, carry objects, and maintain balance across varied landscapes. Yet it also means that certain parts of the spine must absorb pressures far greater than those experienced by the spines of most other mammals. The lower back, particularly the lumbar vertebrae, becomes the region where these forces concentrate most strongly. Positioned between the upper body and the pelvis, this section of the spine acts as a transitional point where weight from the torso is transferred to the legs. When a person stands still, the lumbar vertebrae support much of the body's mass. When the body bends forward, lifts a load, or twists, additional forces pass through this same region. Over a lifetime of movement, these repeated stresses can gradually influence the structures that make up the spine. The discs between the vertebrae compress slightly with each step and expand again when the body rests. Ligaments stretch and tighten as posture shifts. Muscles surrounding the spine contract continuously to maintain balance. None of these processes necessarily indicate damage. They represent the normal operation of a complex mechanical system. However, the vertical orientation of the human spine means that even ordinary activities generate compressive forces that accumulate over time. In quadrupedal animals, the situation differs. Because the body is carried horizontally, gravity acts across the length of the torso rather than directly downward through the spine. Limbs positioned at both ends of the body share the load, while the spine coordinates movement between them. Muscles and tendons absorb much of the energy produced by running or jumping before it reaches the vertebrae. The backbone, therefore, participates in locomotion but rarely bears the full vertical weight of the body in the same concentrated way seen in humans. Observing this contrast helps explain why upright posture represents both an evolutionary advantage and a structural compromise. The ability to stand and walk on two legs freed the hands, improved visibility across open landscapes, and allowed early humans to travel efficiently across long distances. These benefits likely played an important role in the survival and spread of human ancestors across different environments. Yet the skeletal system supporting this posture had to adapt an ancient structure to a new mechanical role. The vertebrae that once functioned within a horizontal framework gradually became components of a vertical column. Evidence from fossil remains shows that natural selection responded to this challenge by modifying certain features of the human spine. Lumbar vertebrae grew broader to support increased loads, while the curvature of the spine helped distribute pressure more evenly during walking. Strong ligaments and muscles evolved to stabilize the torso above the pelvis. These adjustments allowed upright movement to function effectively enough for human populations to thrive. Even so, the underlying architecture remained rooted in a much older evolutionary design. The spine of a human continues to operate within a delicate balance between structural support and mechanical strain. Each step, each movement, and each shift in posture reflects this ongoing negotiation between gravity and the bones that hold the body upright. When a body moves upright through the world, balance becomes a constant process rather than a fixed state. Each step forward requires the body to shift its weight from one leg to the other while keeping the upper body steady above the pelvis. This continuous adjustment is subtle, often unnoticed in daily life, yet it relies heavily on the structures surrounding the spine. Muscles in the abdomen, back and hips work together to stabilize the trunk so that the head and chest remain aligned as the legs move beneath them. In an upright posture, these muscles must remain active even when the body appears still. Standing quietly involves a delicate coordination of small muscular contractions that prevent the torso from leaning too far in any direction. The spine sits at the center of this system, acting as the framework that allows these forces to pass through the body while maintaining balance. In quadrupedal animals, the situation differs in several important ways. Because the body is supported by four limbs, balance during movement is distributed across a broader base. When a horse or dog walks, the limbs move in coordinated patterns that keep multiple points of contact with the ground at nearly all times. The torso remains suspended between these limbs, and the spine functions as a flexible beam connecting the front and rear halves of the body. Muscles along the back guide movement, but do not need to stabilize a tall vertical column in the same continuous manner required in humans. Gravity pulls downward on the animal's body, yet the load spreads outward through the limbs rather than concentrating in a narrow vertical line. This difference becomes especially noticeable when considering how forces travel through the spine during common movements. In a quadrupedal mammal, bending the back usually occurs along the horizontal axis of the body. The spine flexes and extends as the animal runs or leaps, with the motion distributed along many vertebrae. In humans, bending forward or twisting often directs forces through specific regions of the spine, particularly the lower back. Because the upper body sits directly above the pelvis, movements that involve lifting, reaching, or carrying objects create additional pressure within the lumbar vertebrae and the discs between them. These structures must absorb both the weight of the body and the extra forces generated by motion. The muscles that surround the spine play a crucial role in managing these stresses. Strong abdominal and back muscles can reduce the amount of pressure transferred directly to the vertebrae by supporting part of the load themselves. This muscular support acts like a dynamic brace that adjusts with each movement. However, the underlying mechanical arrangement remains different from that of animals whose bodies are oriented horizontally. In humans, the spine continues to function as the central axis of posture, and many forces ultimately travel through its stacked bones. Archaeological evidence suggests that early human populations were already living with these mechanical realities long before the appearance of modern lifestyles. Skeletal remains from prehistoric sites occasionally show signs of vertebral wear, small fractures, or changes associated with repeated physical labor. These findings do not necessarily indicate widespread suffering, but rather reveal that the spine has long been engaged in managing the demands of upright life. Early humans carried loads, gathered food, and traveled across varied terrain while relying on a skeletal structure originally shaped in a different evolutionary context. Through countless generations, natural selection refined this structure enough to support the distinctive posture of humans. Yet the spine never became an entirely new creation. It remained an adaptation built upon an older framework, one that had evolved for bodies moving horizontally across the ground. Understanding this layered history helps clarify why the human spine exists in a state of careful balance. It performs the demanding task of supporting a vertical body while still reflecting the ancient design from which it emerged. The longer a structure performs a task slightly different from the one for which it originally evolved, the more clearly the limits of that structure begin to appear. In the case of the human spine, those limits are most visible in the lower back. This region sits between the weight of the upper body and the powerful movements of the legs, making it the place where forces from both directions converge. Each time a person stands, walks, bends forward, or lifts an object, the lumbar vertebrae absorb pressure that travels downward from the torso, while also responding to motion generated by the hips and legs. Over the course of a day, these forces repeat thousands of times, often without conscious awareness. The spine is designed to handle such repetition, yet the mechanical demands placed upon it remain different from those experienced by most other mammals. The vertebrae in the lumbar region are larger than those found higher in the spine, reflecting the greater loads they must carry. Between them lie discs that act as flexible cushions. These discs contain a gel-like interior, surrounded by layers of tough fibers arranged in rings. When pressure increases, the interior shifts slightly outward, while the outer fibers hold the structure together. This arrangement allows the disc to absorb compression and distribute it across the surrounding vertebrae. In a young and healthy spine, this system operates smoothly, permitting the body to move with both stability and flexibility. Yet the design also means that the discs gradually experience wear as years of movement accumulate. Small changes in the structure of the disc can occur as the inner material loses moisture and the outer fibers endure repeated tension. Such changes are a natural part of aging rather than a sudden failure of the body. Archaeological studies of ancient human skeletons show that signs of disc compression and vertebral remodeling were already present in individuals who lived thousands of years before modern medicine or sedentary work. These findings suggest that the spine has long carried the marks of upright life. The difference between humans and most other animals becomes clearer when examining how their bodies interact with gravity over long periods of time. In quadrupedal mammals, the weight of the torso spreads across 4 limbs and a broad network of muscles. Even when these animals run or leap, the forces created by movement are distributed across the entire body. The spine participates in locomotion but rarely functions as the primary pillar holding the body upright for extended periods. In humans, however, standing itself places continuous load upon the vertebral column. When the body remains upright for long stretches of time, the spine supports the full mass of the head, chest, arms, and internal organs. Muscles help maintain this posture, yet gravity continues to act directly through the stacked vertebrae. This does not mean that the human spine is poorly designed. In many ways, it represents an impressive adaptation that allows an animal originally built for horizontal movement to thrive while standing and walking on two legs. The curves of the spine, the strength of the lumbar vertebrae, and the resilience of the intervertebral discs all contribute to a system capable of supporting the demands of human life. At the same time, these adaptations exist within the limits of a structure inherited from much earlier ancestors. The spine carries both the advantages of upright posture and the mechanical consequences that accompany it. Recognizing this dual nature helps explain why the human body can move with remarkable endurance, while also remaining sensitive to the stresses placed upon its central column. Within that balance lies the quiet cost of an evolutionary change that reshaped the relationship between the human body and gravity. Across the animal world, movement often appears effortless. A wolf can travel long distances across uneven ground, with its back remaining stable. A deer leaps over obstacles without pausing to stretch its spine afterward. Even large animals such as horses can run at high speed across open plains, with little sign that the structure of the back is under strain. These observations raise a quiet question. If the vertebrate spine is shared by so many species, why does persistent back pain appear far more frequently in humans than in most other animals? Part of the answer lies in the way animal bodies interact with gravity during ordinary movement. In quadrupedal mammals, the trunk of the body is suspended between the front and rear limbs. The spine stretches horizontally from shoulders to hips, supported by strong muscles and ligaments that distribute forces along the entire length of the back. When the animal walks or runs, the limbs contact the ground in a pattern that keeps the body balanced across several points at once. Each step sends forces through the legs before they reach the spine. The result is a system where the backbone participates in motion, but rarely acts as the single structure carrying the full vertical weight of the body. Instead, the limbs function like pillars positioned at both ends of the torso. These pillars absorb impact and redirect energy through muscles and tendons before it reaches the vertebrae. Because the body remains oriented horizontally, gravity acts across the length of the torso rather than compressing the spine from above. Even during powerful movements such as jumping or galloping, the spine bends and extends in ways that spread stress across many vertebrae at once. No single segment of the spine must consistently support the entire mass of the animal. This arrangement also influences how animals rest and recover from daily activity. Many quadrupeds spend large portions of time lying down or moving intermittently rather than remaining upright for extended periods. When they do stand, the load is shared among four limbs that naturally form a wide base of support. The muscles surrounding the spine therefore experience different patterns of activity compared with those in humans. Instead of constantly stabilizing a vertical column, they guide motion across a suspended structure supported at multiple points. Even among primates, the closest relatives of humans, similar principles remain visible. Chimpanzees and gorillas possess spines that resemble the human spine in overall composition, yet their typical posture keeps the torso angled forward. When they move across the ground, their arms and legs share the task of supporting body weight. The spine connects these limbs and allows flexibility for climbing and reaching, but it does not function primarily as a vertical pillar supporting the entire upper body. As a result, the forces acting on their vertebrae follow directions closer to those experienced by other quadrupedal mammals. This does not mean that animals never experience spinal problems. Injuries can occur after falls, collisions, or extreme exertion. Certain breeds of domestic dogs even develop spinal conditions related to the length of their bodies or the shape of their vertebrae. Yet widespread chronic back pain affecting large portions of a species appears relatively uncommon outside of humans. The difference emerges from the way posture shapes the mechanical environment of the spine. Humans stand and walk with the body balanced above a narrow column of vertebrae. Most other mammals continue to move with the trunk suspended horizontally between limbs. These contrasting orientations place the same basic structure into very different relationships with gravity. Understanding this distinction helps clarify why the human spine carries a set of mechanical challenges rarely shared by other animals, even though the bones themselves remain part of the same ancient evolutionary design. Another difference between humans and most other animals appears in the rhythm of daily movement. In the natural environments where vertebrate bodies evolved, movement was rarely confined to a single posture for long periods. Animals walk, run, rest, stretch, and change position frequently as they search for food, avoid predators, or explore their surroundings. These shifting patterns of motion continuously redistribute forces across the muscles and joints of the body. The spine participates in these movements as a flexible structure, rather than remaining fixed in one alignment for extended durations. In quadrupedal mammals, this constant variation plays an important role in maintaining the balance of forces along the back. When a wolf trots across a landscape, its spine bends and extends rhythmically with each stride. Muscles along the back contract in coordinated patterns that guide the motion of the vertebrae. When the animal stops to rest, the posture of the spine changes again as the body lowers to the ground or curls slightly during sleep. These repeated adjustments prevent pressure from concentrating in a single region of the spine for long stretches of time. Even the simple act of shifting from standing to lying down alters how gravity interacts with the body, giving tissues opportunities to recover from the stresses of movement. The bodies of large grazing mammals illustrate the same principle in a different form. Animals such as horses or antelope spend long hours moving slowly while feeding. Their heads lower toward the ground, their backs remain aligned with the horizontal plane of the body, and their limbs share the load of supporting the torso. Periods of stillness alternate with periods of walking or running, creating a natural cycle in which the forces acting on the spine are constantly changing direction and intensity. This dynamic pattern reflects the environment in which the vertebrate skeleton evolved, where survival depended on continuous interaction with varied terrain and shifting sources of food. Human movement historically followed similar patterns during much of early evolution. Archaeological evidence suggests that hunter-gatherer populations often traveled significant distances while foraging, gathering plants, or tracking animals. The body remained active across many types of motion: walking, squatting, climbing, lifting, and carrying. These varied activities spread mechanical stress across different muscles and joints rather than concentrating it in a single posture. Within such lifestyles, the spine experienced movement across a wide range of angles and positions. Each change of posture allowed certain tissues to relax while others engaged, creating a balance that helped maintain the flexibility of the vertebral column. The difference between humans and other animals becomes more apparent when the posture of the trunk is considered. In quadrupeds, the spine functions as a horizontal connector linking the front and rear halves of the body. Movement in one region naturally influences movement in another, encouraging the entire structure to participate in locomotion. In humans, the vertical arrangement of the spine places greater emphasis on stability. The torso must remain balanced above the pelvis, even while the legs step forward and the arms perform tasks. This requirement encourages muscles along the back to remain active for long periods, stabilizing the upright column against gravity. Over time, this constant stabilization can create localized strain, particularly in the lower back where the forces of posture and motion converge. Observing animals in their natural environments therefore reveals more than a difference in anatomy. It highlights a difference in how movement interacts with the design of the spine. Quadrupedal bodies continue to use the backbone in ways closely aligned with its ancient evolutionary role. The human body, while remarkably adaptable, asks the same structure to perform a new task as the central pillar of an upright posture. Within this shift lies an important part of the explanation for why the experience of back discomfort appears far more common in humans than in most other species. Another factor that separates the human spine from that of most other animals appears in the length of time the body remains upright during ordinary life. For a quadrupedal mammal, standing is only one of many positions the body regularly adopts. Animals often alternate between standing, walking, lying down, and stretching as part of their natural rhythm. When a dog rests, its spine curls or lengthens along the ground, removing much of the weight that had previously been supported by its limbs. When a horse lies down to sleep, the orientation of its spine shifts entirely, changing the way gravity interacts with the vertebrae and discs. These transitions allow tissues within the back to experience periods of reduced pressure. Over time, such variation helps maintain the balance between loading and recovery that biological structures rely upon. In humans, the pattern of posture evolved differently as upright walking became central to survival. The ability to stand and travel long distances on two legs meant that the spine frequently remained in a vertical orientation for extended periods. While early human populations certainly rested, squatted, and moved in many ways throughout the day, the fundamental arrangement of the body still placed the torso above the pelvis whenever individuals were standing or walking. This meant that the vertebral column regularly supported the combined weight of the head, chest, arms, and internal organs. The muscles of the back and abdomen assisted in maintaining this posture, yet gravity continued to act downward through the stacked vertebrae. This persistent vertical loading represents a condition rarely encountered by animals whose bodies remain horizontal. Even primates closely related to humans typically lean forward while moving across the ground. Their arms and legs share the responsibility of supporting body weight, allowing the spine to function more as a connector than as the central pillar of posture. The contrast becomes clearer when examining the structure of the lower back. Humans possess a relatively long lumbar region composed of several vertebrae capable of forming a pronounced curve. This curvature helps position the torso above the hips, allowing the body to remain balanced while standing. In chimpanzees and gorillas, the lumbar region is shorter and less curved. Their trunks tilt forward during movement, maintaining a mechanical relationship with gravity that resembles other quadrupedal mammals. Because of this arrangement, the forces acting on their spines travel in directions that differ from those experienced in the human body. Observations from veterinary medicine offer another perspective on this difference. Animals can suffer injuries or degenerative conditions of the spine, particularly when their bodies experience unusual strain or trauma. Certain dog breeds with elongated backs, for example, may develop disc problems associated with the shape of their skeleton. Yet widespread chronic back pain affecting large portions of a population remains far more commonly reported among humans. This contrast suggests that the human spine operates under mechanical conditions that are relatively uncommon elsewhere in the animal kingdom. The upright posture that defines the human body places a continuous demand on the vertebral column to support vertical loads over many years of life. Muscles, ligaments, and discs work together to manage these forces, but the basic arrangement still reflects an evolutionary compromise. A structure originally shaped for horizontal movement now functions as the central support of an upright body. Through millions of years of adaptation, this system became capable of sustaining human mobility across varied environments. Yet the difference between this vertical orientation and the horizontal design seen in most other animals remains an important part of the deeper story behind why the human experience of back discomfort appears so distinctive among living species. Long before cities, roads, or permanent settlements existed, the human body developed within landscapes that required constant movement. Early members of the human lineage did not remain in one location for long stretches of time. They moved across valleys, riverbanks, forests, and open grasslands in search of food, water, and shelter. These environments shaped the rhythm of daily life in ways that influenced how the spine was used throughout the day. Walking became one of the most important forms of human movement. Anthropological studies of hunter-gatherer societies suggest that individuals often traveled several kilometers each day while gathering plants, tracking animals, or relocating temporary camps. The body adapted to this pattern of mobility. Long legs, balanced posture, and an efficient stride allowed humans to move steadily across varied terrain while conserving energy. Within this system, the spine served not only as a support for the upper body, but also as a flexible structure that helped coordinate movement between the head, torso, and legs. With each step, the body rises and falls slightly, creating a rhythmic motion that travels through the skeleton. The curves of the human spine help soften these movements, allowing the head to remain relatively stable while the legs absorb the impact of contact with the ground. This stabilization is important for vision and balance. A steady head allows the eyes to focus clearly while walking, making it easier to navigate uneven ground or detect distant objects in the environment. In many ways, the human spine functions as part of a system designed for endurance movement rather than short bursts of speed. Compared with many quadrupedal mammals, humans are not among the fastest runners. However, the human body demonstrates unusual efficiency during long periods of steady travel. Some researchers have suggested that early humans may have used a strategy sometimes called persistence hunting, where individuals follow an animal for long distances until it becomes exhausted. Whether or not this method was widespread, the physical traits of the human skeleton clearly support sustained movement across landscapes. The spine plays a quiet but essential role in this endurance, Its curves absorb the repeated impacts of thousands of steps, while muscles along the back and abdomen maintain stability as the body shifts weight from one leg to the other. Archaeological evidence reinforces the idea that early humans lived within environments that demanded frequent mobility. Stone tools found across large geographic areas indicate that human groups often moved through wide territories. Campsites appear and disappear across layers of sediment, suggesting temporary habitation rather than permanent settlement. These patterns reveal a lifestyle in which walking and carrying were routine parts of survival. Within such conditions, the spine was rarely held in a single fixed posture for long periods. The body alternated between walking, squatting, climbing, bending, and resting. Each activity placed slightly different forces on the vertebrae and discs, distributing mechanical stress across many parts of the body. This variety of movement helped maintain flexibility within the spinal column. Instead of remaining locked in one orientation, the spine continually adjusted to the demands of the environment. Such patterns may have allowed the body to manage the stresses associated with upright posture more effectively. The human spine evolved not only to support standing, but also to participate in a wide range of movements across natural landscapes. It developed within a lifestyle where motion was frequent and varied, and where gravity interacted with the body through changing postures rather than prolonged stillness. Understanding this context reveals an important aspect of the spine's evolutionary story. The structure that supports the upright human body was shaped within an environment defined by movement. Its curves, muscles, and discs were all influenced by the rhythm of walking across open terrain and adapting to shifting conditions of daily life. Life within early human environments involved more than simply walking across open landscapes. Daily survival required a wide range of movements that repeatedly changed the position of the spine throughout the day. Gathering edible plants often meant bending toward the ground, reaching outward, or squatting for extended periods while sorting seeds, roots, or fruits. Hunting and tracking animals required careful movement across uneven terrain, sometimes climbing over rocks or moving through dense vegetation. Carrying food or tools back to temporary camps placed additional demands on the body, shifting weight across the shoulders, arms, and back. Within these activities, the spine rarely remained in a single posture for long. It bent, rotated, and extended as the body adapted to the demands of each task. These patterns of motion distributed mechanical stress across different regions of the vertebral column rather than concentrating it in one place. Squatting, for example, changes the angle of the pelvis and reduces the vertical pressure that passes through the lower back while standing. Climbing or reaching overhead engages muscles along the upper back and shoulders, altering how forces travel through the thoracic region of the spine. Even the simple act of sitting in natural environments often involved postures quite different from the upright seated position common today. People might rest on the ground with the hips flexed, knees bent, or legs folded beneath the body. Each posture shifts the relationship between gravity and the vertebrae, allowing different tissues within the back to alternately engage and relax. The human spine evolved within this dynamic environment of constantly changing movement. Muscles surrounding the vertebrae developed the ability to stabilize the trunk while still allowing flexibility across many directions. The discs between vertebrae experienced cycles of compression and release as the body alternated between standing, walking, and resting. Over long periods, this variation may have helped maintain the balance of pressure within the spinal column. Tissues that experience changing loads often recover more effectively than those subjected to the same forces without interruption. Archaeological evidence supports the idea that early humans used a broad repertoire of body positions. Wear patterns on ancient bones sometimes reveal the stresses associated with kneeling, squatting, or repetitive bending. Tools found at archaeological sites suggest activities that required fine hand movements, while the body remained close to the ground. These clues indicate that daily life involved a range of postures quite different from the more standardized positions seen in many modern settings. The spine participated in each of these movements as a flexible structure connecting the head, torso, and limbs. Its curves allowed the body to shift weight smoothly, while maintaining balance across varied terrain. The muscles of the abdomen and back provided stability when lifting or carrying objects, yet they also relaxed when the body rested or changed position. This constant alternation between effort and release helped maintain the resilience of the vertebral system. In such environments, the upright posture of humans did not operate in isolation. Standing and walking formed only part of a broader cycle of movement that included bending, squatting, climbing, and resting. The spine functioned within this cycle as a structure designed for versatility rather than rigidity. Over thousands of generations, natural selection favored bodies capable of managing these shifting demands while maintaining mobility across large landscapes. The resulting spine reflects this history of varied movement. It carries the imprint of a lifestyle in which posture changed frequently, and the body remained closely connected to the rhythms of the surrounding environment. The landscapes in which early humans lived were rarely smooth or predictable. Paths across the land often passed through uneven ground, scattered stones, fallen branches, and shifting soil. Moving through such environments required constant adjustments of posture and balance. Each step placed the feet on surfaces that differed slightly in height or firmness. The body responded by making small corrections in the position of the hips, knees, and spine. These adjustments were subtle yet continuous, allowing the center of gravity to remain stable while the terrain changed beneath the feet. In this context, the spine functioned as part of a dynamic system that responded to movement rather than remaining fixed in one alignment. The muscles surrounding the vertebrae constantly adapted to maintain balance, contracting and relaxing in response to the shifting position of the body. Walking across uneven terrain therefore engaged the entire back in a coordinated effort that distributed forces across many structures. Instead of concentrating pressure in a single region, the spine shared mechanical demands with the legs, pelvis, and trunk muscles. This pattern differed significantly from movement across flat and uniform surfaces. When the ground beneath the feet varies, the body rarely repeats the same motion exactly. Each step differs slightly from the previous one, altering the direction and magnitude of forces acting on the skeleton. Such variation can help prevent repetitive stress from accumulating in one location. The spine bends, twists, and straightens in response to these changes, maintaining flexibility through constant small adjustments. Early human mobility likely involved many hours of such walking across natural landscapes. Evidence from archaeological and anthropological research suggests that human groups often traveled through territories that included hills, riverbanks, forest edges, and open plains. These environments required attention not only to direction but also to the stability of each step. Carrying food, tools, or infants added further complexity to movement, shifting the distribution of weight across the body. Within these conditions, the spine worked continuously to maintain equilibrium. Its curves helped absorb the vertical forces generated by walking, while surrounding muscles stabilized the torso during shifts in balance. Even during rest, the body often adopted positions that reflected the irregularity of the environment. Sitting might occur on stones, logs, or the ground itself, leading to a variety of postures rather than a single standardized position. Sleeping arrangements could involve lying on uneven surfaces, sometimes curled or angled depending on available space. These variations meant that the spine rarely remained in a rigid alignment for long periods. Instead, it adapted to the contours of the surrounding landscape, engaging different muscles and joints as posture changed. Over thousands of generations, this close relationship between movement and environment influenced the way the human spine functioned. The structure developed within a lifestyle characterized by frequent motion, varied terrain, and diverse postures. Muscles of the back and abdomen supported the spine as it adjusted to these conditions, creating a balance between stability and flexibility. This evolutionary background suggests that the spine was shaped not simply for standing upright but for moving through complex landscapes where posture changed constantly. The vertical orientation of the human body existed alongside a rhythm of bending, reaching, squatting, and walking across irregular ground. Within such a world, the spine remained active and adaptable rather than fixed in a single position. The story of human mobility, therefore, includes more than the shift to walking on two legs. It also reflects the environments through which early humans traveled and the varied movements required to navigate them. When archaeologists study ancient human skeletons, they are often looking for quiet traces of how bodies moved through their environments. Bones carry subtle marks left by years of activity. Joints can reveal patterns of repeated motion, and the surfaces of vertebrae sometimes display signs of stress that accumulated over a lifetime. These traces allow researchers to glimpse how the human spine functioned long before written records or modern medicine existed. One of the most common observations in prehistoric human remains involves small changes in the vertebrae of the lower back. In some skeletons, the edges of the vertebrae show areas where bone has slowly thickened. These formations, often described as osteophytes or small bony growths, develop when joints experience repeated mechanical loading over long periods. They do not necessarily indicate severe pain during life, but they do show that the spine was responding to ongoing physical demands. Similar patterns appear in skeletal remains from many different archaeological sites, suggesting that such changes were a normal part of living with an upright spine. The presence of these features in ancient populations offers an important perspective. They appear in individuals who lived thousands of years before the introduction of chairs, desks, or modern work environments. Many of these people lived as hunter-gatherers or early farmers, moving frequently across landscapes and performing physically demanding tasks. Their daily activities involved carrying materials, preparing food, gathering plants, and traveling across uneven terrain. The spine in these contexts remained active and adaptable, responding to the physical realities of survival. Archaeological studies of early farming communities reveal additional patterns that help illuminate how the spine was used. When agriculture began spreading across parts of the world roughly 10,000 years ago, human populations started to adopt more settled lifestyles. Fields required repeated bending while planting or harvesting crops. Grinding grain with stone tools involved rhythmic upper body movements that were repeated many times each day. Skeletal remains from these communities sometimes show distinctive wear in the joints of the spine and shoulders, reflecting these repetitive tasks. Such findings demonstrate that the mechanical demands placed upon the spine have changed across different historical periods. Yet even within these early agricultural societies, the body continued to experience a wide range of movements. Farming required lifting, carrying, walking, and working close to the ground. The spine bent forward during planting and straightened again while transporting materials. These alternating positions allowed different parts of the vertebral column to participate in the work of daily life. The skeleton therefore records not only stress but also adaptability, showing how the spine managed varied physical demands. Another important source of information comes from the age distribution of ancient populations. Many prehistoric communities included individuals who lived into middle age or beyond, providing researchers with opportunities to examine how the spine changed over decades of activity. In these skeletons, the vertebrae sometimes show signs of gradual remodeling, where bone responded to long-term pressure. These changes reveal that the spine is not a static structure. It adapts continuously to the forces placed upon it, reshaping itself in small ways throughout life. When viewed across many archaeological sites, these patterns form a consistent picture. The human spine has always operated under the influence of gravity and movement. Even in societies far removed from modern lifestyles, the vertebrae carried the marks of upright posture and physical labor. These skeletal clues remind researchers that the experience of spinal stress did not begin in recent history. It emerged alongside the very posture that defines the human body. When archaeologists compare skeletons from different periods of human history, subtle differences begin to appear in the vertebrae and joints of the spine. These differences often reflect the changing ways in which people lived, worked, and moved through their environments. Bones respond gradually to the forces placed upon them. Over time, repeated movements leave small traces that researchers can observe centuries or even thousands of years later. The vertebrae of the spine are particularly sensitive to such long-term mechanical influences. In some ancient skeletons, the surfaces of the vertebral joints appear slightly polished or thickened, suggesting that the bones experience steady pressure throughout life. These patterns can help researchers reconstruct aspects of daily activity. For example, populations that relied heavily on grinding grain with stone tools often show distinctive wear in the shoulders, elbows, and sometimes the upper spine. The repetitive motion of pushing and pulling grinding stones required sustained engagement of the back and arm muscles. Over many years, the vertebrae adapted to these repeated stresses. Similarly, skeletal remains from communities that carried heavy loads may show subtle changes in the lower back, where weight passed from the upper body into the pelvis and legs. One of the most informative discoveries in archaeological research is that such patterns appear in many different cultural and geographic settings. Skeletons from ancient Africa, Europe, Asia, and the Americas sometimes display comparable signs of spinal adaptation. Although the specific tasks performed by individuals varied across societies, the underlying mechanical demands of upright posture remained constant. The spine continued to support the head, chest, and arms while people walked, lifted, or carried objects throughout their lives. In this way, the vertebral column acted as a central structure connecting many forms of physical activity. The evidence also reveals something important about the resilience of the human body. Despite the stresses associated with daily labor, many individuals lived long enough for these skeletal adaptations to develop gradually over time. Bone remodeling occurs slowly, often reflecting years or decades of repeated motion. The presence of these changes in archaeological remains suggests that the spine was capable of functioning effectively even under demanding conditions. Instead of breaking or failing quickly, it responded to stress by reinforcing certain areas and reshaping others. This ability to adapt helped human populations survive within environments that required physical endurance and mobility. At the same time, the archaeological record reminds researchers that the spine has always operated within the limits of a structure shaped by deep evolutionary history. The vertebrae and discs were inherited from ancestors whose bodies moved horizontally across the ground. When humans adopted an upright posture, these ancient components took on new responsibilities. The vertical orientation of the body placed additional compression on the lower back, and over long periods this pressure left visible marks on the skeleton. Even so, these marks often represent gradual adjustments rather than sudden injury. They illustrate the continuous negotiation between biological design and the mechanical realities of life on two legs. By examining these skeletal traces, archaeologists gain insight into how human bodies interacted with the environments in which they lived. Each vertebra becomes part of a larger story describing how people moved across landscapes, performed daily tasks, and adapted to changing ways of life. Through these silent records preserved in bone, the long partnership between the human spine and the demands of upright existence becomes visible across thousands of years of history. Archaeological evidence does more than reveal the stresses placed on the spine. It also offers insight into how the human body endured those stresses across long periods of time. When researchers examine skeletons recovered from ancient burial sites, they often notice that many individuals lived for decades while carrying the physical traces of demanding work. The vertebrae may show gradual thickening, small bony projections, or slight compression of the discs, yet the rest of the skeleton indicates that the person continued to move and function throughout life. These findings suggest that the spine has long possessed a remarkable capacity for adaptation. Bone is a living tissue that responds to the forces acting upon it. When pressure increases in a particular region, the body may reinforce that area by slowly adding new bone. This process occurs over many years and can alter the shape of vertebrae in subtle ways. The spine, therefore, records a kind of physical memory of the activities performed during life. In ancient populations, this memory often reflects a pattern of steady movement and varied labor rather than prolonged immobility. Many skeletons from prehistoric and early historic periods display signs of spinal adaptation without clear evidence of catastrophic injury. This pattern indicates that daily physical activity was intense, but also distributed across different motions. People walked across landscapes, bent to gather plants, lifted objects, and carried materials. These movements repeatedly engaged the muscles supporting the spine, helping maintain stability while the vertebrae gradually adjusted to mechanical demands. In such environments, the spine functioned within a dynamic system of muscles, ligaments, and bones that shared the work of supporting the body. Another important observation comes from the posture implied by certain skeletal features. In some ancient populations, the hip joints and lower limbs suggest frequent squatting or kneeling during daily tasks. These positions change the angle between the pelvis and the spine, reducing the vertical pressure on the lower back compared with standing upright. Squatting places the hips and knees in a flexed position while allowing the torso to remain balanced above the feet. The spine still participates in maintaining posture, yet the load passing through the lumbar vertebrae shifts in direction and intensity. This variation may have provided periods of relief for structures that otherwise carried the body's weight during walking and standing. The archaeological record therefore reveals an important pattern. While the human spine has always experienced mechanical stress, The context in which that stress occurred often involved diverse movements and postures. Instead of maintaining a single rigid alignment throughout the day, ancient bodies alternated between many forms of activity. Each posture engaged different muscles and changed the distribution of forces along the vertebral column. This variation may have helped the spine remain resilient across long lifetimes, even in environments where survival required considerable physical effort. These findings remind researchers that the story of the human spine cannot be understood only through anatomy. It must also be viewed through the behaviors and environments that shape daily life. The bones preserved in archaeological sites show that upright posture has always carried mechanical consequences, yet they also demonstrate the adaptability of the human body. Through thousands of years of movement across varied landscapes, the spine continued to support the posture that allowed humans to explore, gather, and survive in many different regions of the world. Within those ancient bones lies a quiet record of how the body managed the balance between endurance and strain while living with the legacy of upright walking. For most of human history, movement remained closely connected to the rhythms of the surrounding landscape. People walked across fields, gathered food, built shelters, and rested in positions shaped by the terrain around them. This pattern began to change gradually when human communities started to settle in one place for longer periods of time. Around 10,000 years ago, in several regions of the world, groups of humans began cultivating plants and domesticating animals. This transition toward agriculture did not happen everywhere at once, yet wherever it appeared, it slowly altered the relationship between the human body and daily movement. Farming required repeated attention to specific plots of land. Seeds had to be planted, weeds removed, and crops harvested at particular times of the year. These tasks often involved bending forward toward the ground for extended periods. Preparing fields meant digging soil, lifting tools, and carrying bundles of harvested plants. Over weeks and seasons, these actions repeated again and again, creating patterns of movement quite different from the more varied motions of earlier foraging lifestyles. The spine played a central role in these activities. When a person bends forward to reach the ground, the angle between the torso and the pelvis changes, shifting pressure through the vertebrae of the lower back. Muscles along the spine engage to control this movement and prevent the body from collapsing under the weight of the upper torso. In moderation, bending is a normal function of the spine, yet when the same motion occurs repeatedly throughout a day, the mechanical forces passing through the lumbar region begin to follow similar pathways over and over again. Archaeological studies of early agricultural populations reveal subtle skeletal changes consistent with these patterns. Vertebrae from some farming communities display signs of repeated compression and joint wear in the lower back. These features do not necessarily indicate widespread suffering, but rather demonstrate that the daily work of cultivation left recognizable marks on the skeleton. Such marks appear alongside other signs of labor, including wear on the knees, hips, and shoulders associated with lifting and carrying materials. These skeletal traces suggest that agriculture introduced a new rhythm of physical activity into human life. Instead of traveling across wide territories in search of food, many people began returning to the same locations day after day to tend crops. Movement still occurred, yet it often revolved around specific tasks performed repeatedly within a relatively small area. The spine remained active within this environment, bending, lifting, and stabilizing the body during agricultural work. However, the variety of postures experienced throughout the day may have been somewhat reduced compared with earlier foraging lifestyles. Another important change accompanied the rise of agriculture. Permanent settlements gradually appeared as people built houses and storage structures near cultivated fields. These settlements created spaces where individuals spent more time indoors or within confined areas of activity. Grinding grain, preparing food, and crafting tools became common tasks performed close to the ground or while seated. Each of these activities involved the spine in different ways, sometimes requiring the torso to lean forward while the arms worked continuously in front of the body. Over generations, such patterns contributed to new mechanical demands on the vertebral column. The spine still reflected its deep evolutionary origins, yet it now functioned within environments that shaped daily movement in increasingly repetitive ways. The agricultural transition therefore marked an important stage in the long relationship between human behavior and spinal mechanics. The upright body that once moved constantly across landscapes began to adapt to rhythms of labor that repeated the same motions day after day within settled communities. As agricultural communities grew larger and more established, daily life began to revolve around tasks that followed predictable seasonal cycles. Fields needed to be prepared at certain times of the year, seeds planted during narrow windows of favorable weather, and harvests gathered before crops deteriorated. These responsibilities created routines that repeated year after year. Within these routines, the human body often performed the same kinds of movements for extended periods. The spine remained deeply involved in these activities, supporting the torso as people bent, lifted, and carried materials associated with farming. One of the most widespread agricultural tasks involved preparing soil for planting. In many early farming societies, this work required tools such as digging sticks, hoes, or simple plows pulled by human or animal power. Using such tools demanded repeated bending of the upper body while the arms and shoulders generated force against the ground. The muscles along the back and abdomen stabilized the spine as these movements occurred. Over time, the vertebrae and discs in the lower back absorbed the mechanical consequences of these repeated actions. Each motion placed pressure on the lumbar region, as the torso leaned forward and then returned to a more upright position. Harvesting crops created similar patterns. Plants often grew close to the ground, requiring workers to bend, kneel, or squat, while gathering grains, roots, or vegetables. Bundles of harvested plants were then lifted and carried to storage areas or processing sites. These tasks engaged the spine in multiple ways. Bending forward changed the angle of the pelvis relative to the vertebrae, while lifting loads added additional compression through the vertical column of the back. Carrying these loads required the muscles surrounding the spine to maintain stability as the body moved across fields or between structures within a settlement. Archaeological evidence from early agricultural populations provides clues about how these routines influenced the skeleton. Some vertebrae from farming communities display signs of joint remodeling and disc compression that differ slightly from those seen in earlier hunter-gatherer remains. These skeletal patterns suggest that the repeated physical actions associated with farming created consistent mechanical stresses over long periods. The bones responded gradually, adjusting to the forces generated by daily labor. Importantly, these changes rarely indicate sudden injury. Instead, they represent slow adaptations of the body to the repetitive demands of agricultural work. Another activity common in agricultural societies involved processing harvested food. Grain often had to be ground using heavy stones before it could be cooked. This task required individuals to push and pull grinding tools rhythmically for long durations. The movement engaged the shoulders, arms, and upper back, while the torso leaned slightly forward to apply pressure. The spine provided stability during these actions, allowing the body to generate steady force against the grinding surface. Over years of repetition, such motions left identifiable patterns of wear in the joints of the shoulders and sometimes along the upper portions of the spine. Despite these changes, it is important to recognize that agricultural communities still maintained a variety of movements throughout daily life. People walked between fields, carried water, gathered firewood, and performed numerous tasks within and around their settlements. The spine remained active across many positions, although certain motions became more repetitive than before. This shift toward repeated patterns of labor marked a gradual transformation in how the human body interacted with its environment. The upright spine continued to function as the central support of posture, yet it now did so within routines shaped by cultivated landscapes and seasonal cycles. Through these changing conditions, the vertebral column carried forward both its ancient evolutionary design and the accumulating traces of new ways of living. As agricultural settlements became permanent features of the landscape, the human relationship with space began to change in subtle ways. Instead of moving continuously across wide territories, many people spent increasing amounts of time within villages, fields, and nearby paths connecting these areas. The body still worked hard, often performing demanding physical tasks, yet the pattern of movement became more centered around particular locations. The spine, which had evolved within a rhythm of constant travel and varied terrain, now operated within environments where the same actions and positions could occur repeatedly across days, months, and years. Within early villages, many tasks required people to remain in one position for extended periods while their hands performed detailed work. Preparing food, shaping pottery, weaving fibers, or repairing tools often involved sitting or kneeling close to the ground. In these positions, the spine remained active, yet the upper body frequently leaned forward while the arms moved rhythmically in front of the torso. This posture placed steady demands on the muscles of the back and shoulders, which worked to stabilize the trunk while the hands performed precise movements. Over time, such positions could produce consistent mechanical loading along particular regions of the spine. The transition to more permanent settlements also introduced built environments that subtly influenced posture. Early houses were often small structures constructed from earth, wood, or stone. Activities such as cooking, grinding grain, or crafting tools occurred inside these spaces, sometimes requiring individuals to sit or crouch for long periods while working near the ground or around low surfaces. These environments did not yet resemble the furniture-filled interiors of modern life, but they still shaped how the body organized itself during daily tasks. The spine adjusted to these conditions by maintaining stability, while the torso remained inclined forward or balanced above bent legs. Archaeological discoveries from agricultural settlements occasionally reveal skeletal patterns consistent with such lifestyles. Vertebrae from some individuals show gradual changes where joints experience repeated loading over many years. These changes appear alongside other indicators of labor in the hips, knees, and shoulders, suggesting that the entire body participated in the physical work of village life. The spine was not isolated from these demands. Instead, it formed part of a network of structures responding collectively to the activities required for farming, food preparation, and tool production. Another subtle shift occurred in the daily rhythm of movement. Earlier foraging lifestyles often involved alternating periods of travel, gathering, and rest across varied landscapes. In agricultural communities, movement still occurred, but was often structured around the routines of tending fields or maintaining households. Tasks repeated within familiar locations, and the body returned to the same work areas day after day. This pattern did not eliminate variation in posture, yet it introduced a degree of repetition that differed from earlier ways of life. The spine remained capable of handling these demands, yet the mechanical environment surrounding it continued to evolve. Through thousands of years of agricultural living, the human skeleton gradually reflected these adjustments. The vertebral column still carried the legacy of upright walking developed millions of years earlier, yet it also bore the marks of new patterns of labor and settlement. These marks remind researchers that the human spine does not exist apart from the environments in which people live. Its structure and condition reflect both ancient evolutionary design and the habits that shape everyday movement. The agricultural world therefore added another chapter to the long history of how the human body adapted to changing landscapes and ways of life. For thousands of years after the beginning of agriculture, human societies continued to rely on physical labor closely connected to the natural environment. Fields were cultivated by hand or with simple tools, materials were carried across short distances, and daily tasks required frequent movement. Although agricultural life introduced repetitive motions, the body still remained engaged in a wide range of activities throughout the day. This balance began to shift more dramatically during a much later period of history known as the Industrial Revolution. Beginning roughly in the 18th century in parts of Europe and later spreading to other regions of the world, industrialization transformed how people worked and moved within their environments. Factories appeared where machines powered by water, steam, and eventually electricity performed tasks once completed by hand. These machines required workers to operate them, often within buildings where production followed strict schedules and repeated processes. The human body gradually adapted to a new rhythm of labor, organized around machinery rather than the cycles of seasons and natural landscapes. Within these industrial spaces, posture often changed in important ways. Many factory tasks required workers to remain in fixed positions while supervising or guiding machines. Some individuals stood for long hours beside mechanical equipment, maintaining steady attention while performing small, repetitive motions with their hands. Others sat on stools or benches while assembling objects, stitching fabrics, or operating tools that required precise and continuous hand movements. In both situations, the spine played a central role in maintaining stability, while the arms and hands carried out the detailed work of production. Unlike the varied motions of earlier agricultural life, these tasks sometimes kept the torso in similar positions for extended periods. The vertebral column supported the upper body while muscles of the back remained engaged to prevent the torso from leaning too far forward or collapsing under the weight of the head and chest. Over time, the mechanical demands placed on the spine began to reflect these new working conditions. Standing in one location for long stretches allowed gravity to act continuously through the stacked vertebrae. Sitting for extended periods placed pressure on the lower back as the pelvis supported the weight of the torso against the surface of a seat. Although the human spine had always managed vertical loads, the duration and repetition of these postures became more pronounced within industrial settings. Historical records from the 19th century occasionally mention physical discomfort among workers whose tasks required long hours in fixed positions. These observations were often informal and lacked the medical detail found in modern studies, yet they provide hints about how the body responded to new patterns of labor. Workers who operated machinery or performed repetitive manual tasks sometimes reported fatigue in the back or shoulders after extended shifts. Such experiences suggest that the human spine was encountering mechanical conditions somewhat different from those of earlier eras. Industrial environments also altered the physical spaces in which people moved. Large buildings replaced open landscapes, and pathways between machines or workstations became the primary routes of daily travel. The ground beneath the feet was often flat and uniform, reducing the small variations in posture that occur when walking across natural terrain. The body still moved, yet the range of movement sometimes narrowed as tasks became more specialized and repetitive. Within this setting, the spine continued to support the upright human body while adapting to a new relationship between posture, labor, and environment. As industrial workplaces expanded during the 19th and early 20th centuries, the organization of labor increasingly shaped how the human body spent its time. Factories often operated according to strict schedules, and workers followed routines designed to keep machines running efficiently. Tasks became divided into smaller steps, each repeated many times throughout the day. This system increased productivity, yet it also influenced how people stood, sat, and moved while performing their work. The spine remained central to these adjustments because it supported the upper body during long periods of controlled, repetitive activity. In many industrial settings, workers stood beside machinery for extended hours. Their attention focused on guiding materials through mechanical processes or monitoring equipment as it operated. The body might remain upright in nearly the same position while the hands and arms performed precise actions in front of the torso. Maintaining this posture required continuous activity from the muscles along the spine. These muscles worked quietly to stabilize the trunk and prevent the body from leaning forward or backward as the arms moved. While the human spine is capable of supporting upright posture, holding that posture with limited variation places steady mechanical demands on the vertebral column. Other industrial tasks involved seated work, textile production, assembly of small components, and certain forms of craftsmanship often required individuals to sit while manipulating tools or materials on a work surface. In these positions, the pelvis rested on a seat while the torso leaned slightly forward to allow the hands to operate in front of the body. The lower back supported the weight of the chest, arms, and head while the muscles of the abdomen and spine maintained balance. Over long shifts, this posture could remain largely unchanged as workers concentrated on repetitive hand movements. The human spine, which had evolved within environments characterized by frequent motion and shifting terrain, now found itself maintaining stability during long periods of stillness. The industrial workplace also introduced surfaces and structures that were far more uniform than the natural landscapes in which human movement originally developed. Factory floors were flat and solid, workstations were arranged in rows, and the space between them rarely changed. The feet often stood or rested on the same level ground throughout the day. Without the small variations of natural terrain, the body repeated similar patterns of posture again and again. These conditions reduced the subtle adjustments that normally occur when walking across uneven ground or shifting between many positions. Historical accounts from physicians and social observers of the period occasionally noted fatigue and discomfort among individuals engaged in prolonged industrial labor. Although the scientific understanding of musculoskeletal health was limited at the time, these reports hinted at the physical consequences of extended standing or seated work. Some workers described stiffness in the lower back or tension across the shoulders after long shifts beside machines or workbenches. Such experiences suggest that the spine was encountering a new mechanical environment shaped by the organization of industrial production. Despite these changes, it is important to recognize that the human body remained capable of adapting to many of these demands. Muscles surrounding the spine continued to stabilize posture, and individuals often developed strength and endurance within the routines of their occupations. Yet the conditions of industrial life marked another stage in the long story of how human behavior influences the mechanical experience of the spine. The upright posture that once evolved within landscapes of varied movement now operated within buildings where tasks repeated in predictable patterns, and the body sometimes remained still for long intervals of time. As industrial societies continued to develop, the structure of daily life gradually shifted beyond the walls of factories. Transportation systems expanded, cities grew larger, and new forms of work appeared that required less direct physical labor. Offices, schools, and administrative institutions became common parts of urban life. These environments introduced another subtle change in how the human body interacted with posture and movement. Instead of standing beside machines or performing agricultural work outdoors, increasing numbers of people spent their time seated while writing, calculating, reading, or organizing information. Within these settings, the spine remained the central support of the body, yet the conditions under which it operated began to differ from those experienced during earlier stages of human history. Sitting had always existed as one of many natural human postures. People could sit on the ground, rest on rocks, or lean against trees while preparing food or repairing tools. In these contexts, sitting was usually temporary and often involved a variety of positions. The hips might be flexed deeply while squatting, or the legs could be folded beneath the body while resting close to the ground. These postures changed frequently as individuals shifted weight or stood to continue moving through their environment. In contrast, the seated posture that became common in offices and schools often involved a chair positioned in front of a desk or work surface. The pelvis rested on a flat seat while the spine rose upward to support the torso. The arms extended forward to reach tools, papers, or writing instruments placed on the surface ahead. This arrangement allowed the hands to perform precise tasks while the body remained relatively still. Although the human spine can maintain this position, holding it for long periods introduces a different pattern of mechanical forces compared with walking or squatting. When sitting, part of the body's weight transfers through the pelvis into the surface of the seat. The lower back often curves slightly forward or backward depending on posture, and the muscles along the spine engage to stabilize the torso above the hips. Over extended periods, the vertebrae and discs experience steady pressure rather than the alternating cycles of movement and relief that occur during more active motion. The modern office environment therefore represents another stage in the evolving relationship between human behavior and spinal mechanics. Unlike agricultural fields or factory floors, offices typically involve long intervals of relatively stationary work. Writing documents, reading texts, or managing information requires concentration rather than large bodily movements. The spine remains upright while the hands and eyes perform the primary actions of the task. Observations from the late 19th and early 20th centuries began to note this shift in posture. Physicians studying the health of office workers occasionally described complaints of stiffness in the neck or lower back after prolonged seated work. Although these observations were often anecdotal, they suggested that the spine was responding to a new combination of posture and duration. The body that had evolved for varied movement across landscapes now spent increasing time maintaining stability while seated indoors. This transformation did not happen suddenly or uniformly across all societies. Many people continued to perform physically demanding work, and even those in offices often moved throughout the day. Yet the gradual rise of sedentary occupations marked another chapter in the story of how human environments influenced the mechanical experience of the spine. The upright column of vertebrae that once stabilized the body during long journeys across natural terrain now also supported the stillness required for written communication and organized administration. Among the many postures the human body can adopt, sitting is one of the most familiar in modern life. Yet from the perspective of evolutionary history, it is a relatively recent habit to remain seated for long, uninterrupted periods. For most of the time that humans have existed, daily movement involved walking, standing, bending, squatting, climbing, and resting in varied positions. Sitting occurred as part of this sequence. but it rarely dominated large portions of the day. In contrast, many modern environments encourage the body to remain seated while performing work, traveling, studying, or relaxing. This shift has quietly altered the mechanical relationship between the spine and gravity. When a person sits, the orientation of the pelvis changes compared with standing. The hips flex as the thighs extend forward, and the base of the spine settles onto the surface of a seat. In this position, part of the body's weight transfers through the pelvis rather than through the legs. The vertebral column continues to support the torso, yet the curves of the spine may adjust depending on how the body is positioned. If the torso leans forward slightly, the lower back may flatten or round, changing the way pressure passes through the discs between the vertebrae. Muscles along the back and abdomen engage to stabilize the body while the arms reach forward to interact with objects placed in front of the body. These mechanical adjustments are not inherently harmful. The human spine possesses a remarkable ability to accommodate many postures. Sitting can offer a useful period of rest after walking or physical activity, allowing certain muscles to relax while others take on supportive roles. The body naturally alternates between positions during everyday movement, shifting weight from one structure to another. Problems tend to arise not from the posture itself, but from the duration for which it is maintained without variation. In many contemporary settings, individuals remain seated for extended intervals while focusing on tasks that require visual attention and precise hand movements. Reading, writing, typing, and viewing screens often occur in front of a desk or table, where the torso leans forward slightly and the head remains oriented toward a fixed point. During such activities, the spine continues to support the upper body, while the legs remain relatively inactive beneath the seat. Because the position changes little over time, certain regions of the spine may experience sustained compression. The lower back often becomes the area where these forces accumulate most noticeably. From an evolutionary perspective, the human spine did not develop within environments characterized by long periods of stillness. The ancestors of humans moved through landscapes where posture shifted frequently as the body responded to terrain, tasks, and social activity. The vertebral column evolved within this dynamic setting, adjusting continuously to changing positions rather than maintaining a single configuration for hours at a time. When modern lifestyles encourage prolonged sitting, the spine operates within mechanical conditions, somewhat different from those that shaped its evolutionary history. Observations from modern health research have drawn attention to this difference. Studies examining spinal pressure have shown that certain seated positions can increase compression in the lower back compared with standing. These findings do not suggest that sitting itself is unnatural, but they highlight how posture interacts with duration and context. The human spine remains capable of supporting seated activity, yet it appears to function most comfortably when movement and variation remain part of daily life. This perspective reflects a broader pattern visible throughout the history of the human body. The spine performs best within environments that allow it to alternate between multiple positions rather than remaining fixed in one arrangement for long periods. When the human body sits for extended periods, the forces acting on the spine begin to follow patterns different from those experienced during standing or walking. The pelvis becomes the primary structure supporting the body's weight, resting directly against the surface of the seat. From this base, the vertebral column rises upward to support the torso, head, and arms. Although the spine is designed to carry weight in a vertical orientation, the arrangement of the pelvis during sitting subtly alters the curvature of the lower back. The natural inward curve of the lumbar spine often becomes reduced or flattened as the hips remain flexed. This shift changes how pressure is distributed across the discs between the vertebrae. In a standing position, the spine maintains its natural curves with the pelvis balanced above the legs. Muscles in the abdomen, hips, and back coordinate to stabilize the trunk while the body moves. When walking, the spine experiences a repeating cycle of compression and release as the body rises and falls slightly with each step. These small changes in pressure allow fluids within the intervertebral discs to move and adjust, helping maintain their flexibility over time. Sitting for long intervals interrupts this cycle. The body remains relatively still while the discs sustain continuous pressure rather than alternating phases of loading and release. The muscles surrounding the spine also respond differently during prolonged sitting. In active movement, these muscles engage and relax in varying patterns as the body shifts position. When seated for extended periods, many of these muscles remain in a steady state of low-level contraction to stabilize the torso. The deeper muscles along the spine work quietly to prevent the body from collapsing forward under the weight of the head and chest. Meanwhile, the shoulders and neck may lean slightly toward the objects or screens placed in front of the body. This posture can gradually increase the demand on the muscles that support the upper spine and the base of the neck. Another aspect of sitting involves the relationship between the spine and the lower limbs. During walking or standing, the legs actively participate in supporting the body's weight and maintaining balance. Muscles in the hips and thighs assist in stabilizing the pelvis, which in turn helps maintain the alignment of the spine. When seated, the legs remain largely inactive while the pelvis rests on a fixed surface. This shift reduces the role of the lower limbs in supporting posture and places greater emphasis on the structures of the spine and surrounding muscles. Over time, this altered distribution of effort may contribute to the sensation of stiffness that many people notice after remaining seated for long intervals. Despite these mechanical differences, it is important to recognize that the human body remains highly adaptable. Sitting itself is not harmful when it occurs as one of many positions used throughout the day. The spine can support seated posture effectively when movement, stretching, and changes in position interrupt periods of stillness. Observations from physiology show that even small adjustments in posture can redistribute pressure within the spine. Leaning back slightly, standing up briefly, or walking a short distance allows the vertebrae and discs to experience new patterns of force. From the perspective of evolutionary history, such variation reflects the environment in which the human spine developed. Early humans rarely maintained a single posture for extended periods. Movement across varied landscapes required the body to shift constantly between positions. The spine evolved within this dynamic context, adapting to motion and flexibility rather than immobility. When modern routines encourage prolonged sitting, the spine continues to function but does so under mechanical conditions that differ from those of earlier human environments. Over long stretches of time, the human spine demonstrates a quiet sensitivity to how the body organizes its daily movement. When posture remains varied, the forces acting on the vertebrae shift from one region to another. Walking distributes weight through the hips and legs while the curves of the spine soften the repeated impacts of each step. Bending engages muscles along the back and abdomen, temporarily altering the direction of pressure through the discs between the vertebrae. Even resting positions such as squatting or lying down change the orientation of the pelvis and allow different tissues to relax. This constant variation forms an important part of how the spine maintains its resilience. Sitting for extended periods alters this rhythm by reducing the range of positions the body experiences throughout the day. Instead of alternating between walking, standing and bending, the spine may remain within a narrow range of angles while the torso faces forward toward a desk or screen. The head stays oriented toward a fixed point, and the arms extend in front of the body while performing small, repetitive actions. Within this arrangement, the muscles supporting the spine remain engaged to stabilize the upper body, yet they do so without the shifting patterns of activity that accompany more dynamic movement. Over time, this steady demand can produce sensations of stiffness, particularly in the lower back and the base of the neck. These sensations do not arise from a single moment of strain, but from the gradual accumulation of mechanical pressure within tissues that have remained in similar positions for long intervals. The intervertebral discs respond to these conditions as well. These discs are designed to act as flexible cushions between the vertebrae, allowing the spine to absorb shock while maintaining mobility. During normal movement, the discs experience alternating cycles of compression and release as the body changes posture. When a person remains seated for long periods, this cycle becomes less pronounced. The discs remain under relatively constant pressure while the surrounding muscles stabilize the torso. Over many hours, the internal fluid within the discs may shift slightly, contributing to the feeling of compression that some individuals notice after prolonged sitting. Observations from modern physiology support this understanding of spinal mechanics. Measurements of pressure within the discs of the lower back show that certain seated positions can create greater compression than standing or walking. The difference arises from the angle of the pelvis and the position of the torso while seated. When the body leans forward without support, the lower back may lose some of its natural curve, allowing more pressure to pass through the front portion of the discs. This mechanical change does not automatically lead to injury, yet it illustrates how posture and duration interact within the structure of the spine. From a broader perspective, these patterns highlight the relationship between the human body and the environments it inhabits. The spine evolved within landscapes where movement occurred across varied terrain, and posture changed frequently throughout the day. The modern world often encourages different habits, including long periods of sitting while working, studying, or traveling. The spine continues to function within these conditions, yet it still reflects the biological heritage of a body designed for movement and variation. Understanding this contrast helps explain why many people experience relief when they stand, stretch, or walk after sitting for extended periods. Such changes restore the shifting patterns of pressure that the spine has managed throughout much of human history. One of the most significant changes in human history has not occurred in the shape of the body, but in the length of life itself. For much of the past, many people did not live long enough to experience the later decades that are now common in many parts of the world. Disease, accidents, limited medical knowledge, and unpredictable environmental conditions meant that life expectancy in many ancient populations was relatively low compared with modern standards. This does not mean that older individuals did not exist. Archaeological records show that some people reached advanced ages even in prehistoric societies, yet the overall number of individuals living into their 60s, 70s, or beyond was much smaller than it is today. This shift in lifespan has important implications for understanding the experience of the human spine. The vertebral column is a structure that functions continuously throughout life. From the moment a child begins to stand and walk, the spine carries the weight of the upper body and responds to the mechanical demands of movement. Over years and decades, the discs between the vertebrae compress and release thousands of times each day. Muscles surrounding the spine engage to stabilize posture, while ligaments maintain alignment between the bones. These processes occur so gradually that they often pass unnoticed in early adulthood. However, as time progresses, small changes accumulate within the tissues that support the spine. The discs slowly lose some of their internal moisture, reducing their ability to rebound after compression. The surfaces of the vertebrae may thicken slightly where joints experience repeated pressure. None of these changes represent sudden damage. They reflect the natural process by which biological structures respond to long-term mechanical use. When individuals live longer, the spine simply has more years in which these gradual adjustments can occur. Historical and archaeological evidence helps illustrate this relationship between age and spinal change. In skeletal collections from ancient populations, vertebrae belonging to older individuals often display more pronounced signs of joint remodeling than those of younger adults. The differences suggest that the passage of time itself plays a role in shaping the structure of the spine. When researchers compare these remains with modern medical imaging of living populations, similar patterns appear. Many adults show mild changes in the discs or vertebrae as they grow older, even when they do not experience significant discomfort. These observations reveal that the human spine is not a static structure, fixed at maturity. It evolves gradually throughout life as it adapts to the forces generated by movement and gravity. The increase in human lifespan during recent centuries, therefore, introduces a new dimension to the story of back pain. In earlier eras, fewer individuals reached ages where the cumulative effects of decades of spinal loading became visible. Today, improvements in nutrition, sanitation, and medicine allow large portions of the population to live well beyond middle age. As a result, the spine continues to operate under mechanical stress for many more years than it once did for most individuals in the past. This does not mean that modern life alone created spinal discomfort. The vertebral column has always carried the physical demands of upright posture. Yet the longer a person lives, the more time there is for small structural changes to accumulate within the bones and discs of the back. The story of the human spine, therefore, includes not only the evolution of posture and movement, but also the changing structure of human populations across history. As lifespans extend, the spine remains active for longer periods, continuing to support the body through decades of daily activity. As human lifespan gradually extended across the past few centuries, the experience of living with the body changed in quiet but meaningful ways. Improvements in food availability, sanitation, and medical care allowed larger numbers of people to reach later decades of life. Within this longer span of years, the spine continued performing the same fundamental task it had always carried out: supporting the weight of the upper body while allowing movement through the world. Yet when a structure functions for many decades, the slow processes of biological change become more visible. The vertebral column is made of bones, discs, ligaments, and muscles that respond continuously to mechanical stress. Each step taken while walking sends small forces through the spine. Each moment spent standing transfers the weight of the head, chest, and arms downward through the vertebrae. Over time, these repeated forces create gradual adjustments in the tissues that support the spine. One of the most well-known changes involves the discs between the vertebrae. These discs contain a soft interior surrounded by layers of fibrous tissue. In youth, the interior holds a high proportion of water, allowing the disc to compress and rebound easily when the body moves. As years pass, the internal composition of the disc slowly shifts. Some of the water content decreases, and the disc may become slightly thinner. This process occurs gradually and is considered part of the natural aging of the spine. The vertebrae themselves also respond to decades of mechanical loading. The edges of the bones may develop small projections where joints experience repeated pressure. These changes reflect the body's attempt to stabilize areas that have endured long periods of stress. The muscles surrounding the spine also evolve across the lifespan. In earlier decades, these muscles often provide strong support that helps maintain posture and balance. Over time, muscle mass may decline slightly if physical activity decreases, altering the distribution of effort required to stabilize the trunk. The relationship between muscles and vertebrae therefore continues to shift as the body ages. Importantly, many of these structural changes appear even in individuals who do not experience significant discomfort. Medical imaging has shown that mild disc thinning or joint remodeling can occur in people who remain active and healthy. These findings suggest that aging of the spine is a complex process influenced by both time and lifestyle. The spine does not simply deteriorate as years pass. Instead, it adapts gradually to the forces it encounters throughout life. In earlier periods of human history, relatively fewer individuals lived long enough for these slow adjustments to accumulate across several decades. Today, however, the number of people living into older age has increased dramatically in many parts of the world. As a result, a greater proportion of the population experiences the long-term effects of decades spent standing, walking, lifting, and sitting within modern environments. The human spine therefore continues its work across a much longer portion of the lifespan than it did for many individuals in earlier eras. This extended timeline reveals aspects of spinal biology that were once less visible within the structure of human populations. The vertebral column carries not only the imprint of evolutionary history, but also the quiet record of years lived within gravity. Each decade adds new layers to that record as the spine adjusts to the mechanical demands of daily life. As more people began living into later decades, the experience of aging with a spine adapted for upright life became increasingly visible within human societies. The vertebral column does not simply endure the passage of time in a passive way. It responds gradually to the forces placed upon it, adjusting the structure of bone, cartilage, and surrounding tissues across many years of activity. These adjustments accumulate quietly, often without drawing attention until the later stages of adulthood when the body begins to reflect the long record of movement carried throughout life. Throughout early and middle adulthood, the spine usually performs its work with little notice. Individuals walk, lift, bend, and sit as part of daily routines while the vertebrae and discs manage the mechanical consequences of these actions. The discs compress and rebound thousands of times each day, absorbing the shocks created by footsteps and shifts in posture. Muscles surrounding the spine stabilize the torso and assist with balance as the body moves through different environments. This continuous interaction between gravity, movement, and biological tissue forms the background of ordinary life with an upright body. Over longer spans of time, however, the cumulative effect of these forces becomes more apparent. The discs between vertebrae gradually change in composition as the years pass. The gel-like interior may lose some of its water content, reducing its elasticity and altering how it responds to compression. Vertebral joints can develop small structural modifications where bone thickens slightly to support areas experiencing repeated pressure. Ligaments that stabilize the spine may also stiffen with age, influencing how the vertebrae move relative to one another. These developments do not occur suddenly or uniformly. Instead, they emerge slowly across decades, reflecting the combined influence of posture, activity, and biological aging. Medical research has shown that many of these structural changes appear in individuals regardless of whether they experience noticeable back discomfort. Imaging studies of healthy adults often reveal disc thinning or mild joint remodeling, even in people who remain active and free of significant symptoms. Such findings highlight the adaptability of the spine. Rather than representing immediate damage, these changes frequently indicate the body's effort to maintain stability as tissues respond to long-term mechanical stress. The modern increase in human lifespan therefore allows these gradual processes to become more common within the population. In earlier eras, fewer individuals reached ages where decades of spinal loading had accumulated to a noticeable degree. Today, many people live long enough for the natural adjustments of the spine to appear more widely across society. This shift does not mean that the spine is failing more often than before. Instead, it reflects the extended duration over which the vertebral column now performs its role supporting the upright body. Each additional decade of life adds further chapters to the story recorded within the bones and discs of the back. Understanding this relationship between lifespan and spinal change offers a broader perspective on why back discomfort appears so frequently in modern populations. The spine carries both the legacy of evolutionary design and the lived experience of many years under gravity. It supports the body through childhood growth, adult movement, and the gradual transformations that accompany aging. When viewed across the full span of human life, the spine reveals itself as a structure shaped not only by evolution but also by time itself. Across the long span of human history, the spine has quietly carried the story of how the body interacts with gravity. It began as a structure shaped within animals whose bodies stretched horizontally across the ground or through water. Over millions of years, that structure was gradually adapted to support a posture rarely seen among mammals. When human ancestors began to walk upright, the spine inherited a new role as the central column of balance for the entire upper body. This transformation allowed the hands to move freely, enabled long-distance travel, and supported many of the behaviors that eventually defined human societies. Yet the same change also introduced a set of mechanical conditions unlike those experienced by most other animals. Gravity began acting directly downward through the vertebrae, rather than across the length of the body. The discs between these bones absorbed compression with every step, and the muscles surrounding the spine worked continuously to stabilize the torso above the pelvis. For thousands of years, this system functioned within environments where movement remained varied and frequent. Early humans walked across uneven terrain, bent to gather food, climbed, carried objects, and rested in positions shaped by the landscape around them. The spine participated in all of these motions, shifting its orientation repeatedly throughout the day. This variety of movement distributed pressure across different regions of the vertebral column, allowing tissues to experience cycles of effort and release. Later stages of human history gradually introduced new patterns of activity. Agricultural communities required repeated tasks such as planting, harvesting, and processing crops. Industrial societies organized work around machines that sometimes kept the body standing or sitting in fixed positions for long hours. Modern environments added further changes as transportation, office work, and digital technology encouraged extended periods of seated activity. Each of these transitions altered how the spine encountered gravity and mechanical stress during daily life. The underlying structure of the vertebral column, however, remained rooted in its ancient evolutionary design. The bones, discs, and ligaments that support the human back still reflect the architecture inherited from distant ancestors. They were shaped within bodies that moved constantly across varied terrain rather than remaining still for prolonged intervals. When modern habits concentrate movement into narrower patterns, the spine continues to function, yet it does so within conditions that differ from those that shaped its earliest adaptations. Another factor adds complexity to this picture. Human populations today include far more individuals living into older age than at most points in the past. As lifespans extend, the spine remains active for many additional years, continuing to support the body through decades of walking, lifting, sitting, and bending. Small structural changes that occur gradually over time therefore become more visible within the population. The vertebrae and discs record these decades of mechanical experience, reflecting the cumulative interaction between biology and environment. When these elements are considered together, a broader understanding begins to emerge. The experience of back discomfort does not arise from a single cause or a sudden failure within the body. Instead, it reflects the complex meeting point between an ancient skeletal design and the changing patterns of human life. The spine carries the legacy of evolutionary transformation, the influence of historical lifestyles, and the accumulated effects of years lived under gravity. Each of these factors contributes quietly to the conditions in which the human back now operates. When these long strands of history are placed side by side, the human spine begins to appear less like a flawed structure and more like a record of adaptation unfolding across deep time. Every vertebra carries traces of earlier evolutionary stages, while every movement in daily life adds another layer to that history. The spine did not begin as a vertical column designed exclusively for upright walking. It emerged from a lineage of animals whose bodies moved horizontally through water, across forest floors and along open ground. When human ancestors gradually adopted bipedal movement, the same skeletal framework was asked to perform a new role while still preserving much of its original architecture. This transformation succeeded well enough for humans to spread across continents, build settlements, and develop complex societies. Yet the adaptation was never absolute. The spine remains an ancient structure operating within a modern body. One way to understand this relationship is to think of the spine as part of a system constantly balancing stability and movement. On one hand, the vertebral column must remain strong enough to support the weight of the upper body while standing or walking. On the other hand, it must remain flexible enough to allow bending, turning, and reaching in many directions. The discs between vertebrae, the ligaments holding them together, and the muscles surrounding the back all cooperate to maintain this balance. Too much rigidity would limit movement, while too little stability would make upright posture impossible. The spine therefore exists in a carefully maintained equilibrium between these opposing demands. Human history has repeatedly introduced changes that influence how this equilibrium is maintained. Agricultural labor encouraged repeated bending toward the ground. Industrial work sometimes required prolonged standing or repetitive manual tasks. Modern environments often encourage extended periods of sitting while the hands and eyes focus on detailed work in front of the body. Each of these patterns shifts the mechanical demands placed upon the spine, yet the underlying biological structure remains largely the same as it was thousands of years ago. The vertebrae still form a stacked column above the pelvis. The discs still cushion the bones as gravity presses downward through the body. Muscles and ligaments continue their quiet task of stabilizing posture. The experience of back discomfort therefore reflects a convergence of influences rather than a single cause. Evolutionary heritage shapes the basic structure of the spine. Cultural and technological developments influence how the body moves or remains still during daily life. Lifespan determines how many years the spine must perform its work supporting the body. Together, these elements create the mechanical environment in which the human back now functions. Medical research increasingly recognizes that the health of the spine often depends on maintaining a balance between activity and rest. Movement encourages circulation within the discs and strengthens the muscles that stabilize the vertebrae. Periods of rest allow tissues to recover from the stresses created by gravity and motion. When daily life contains both elements, the spine operates within conditions similar to those in which it evolved. When posture remains fixed for long intervals, the distribution of forces becomes less varied, and certain tissues may experience sustained pressure. Understanding this relationship does not mean returning to a distant past or abandoning the conveniences of modern life. Instead, it highlights the biological context within which the human spine developed. The body still carries the imprint of environments where movement was frequent and posture changed regularly throughout the day. Recognizing this heritage helps explain why the spine responds positively when movement and variation remain part of ordinary life. When the long arc of human history is viewed together, the experience of back discomfort begins to appear less like a mysterious modern problem and more like a reflection of how the human body has traveled through time. The spine stands at the center of this story. It links ancient evolutionary origins with the daily movements of the present. Every vertebra is shaped by a lineage that began hundreds of millions of years ago in creatures whose bodies moved horizontally through water or across the ground. When the ancestors of humans gradually began walking upright, that ancient structure was placed into a new relationship with gravity. The change brought remarkable advantages. Standing on two legs allowed the hands to carry tools and food, raised the head for a wider view of the environment, and made long-distance travel across landscapes more efficient. These advantages played an important role in the survival and expansion of human populations. Yet the shift also meant that the spine began supporting the body in a way rarely seen among other mammals. Instead of acting as a bridge between limbs, it became the central column balancing the head, chest, and arms above the pelvis. Through thousands of generations, human societies developed within this upright posture. Movement across varied terrain, bending to gather food, carrying materials, and building shelters formed the physical rhythm of daily life. Within these activities, the spine remained active, constantly adjusting to different positions and loads. The variety of movement helped distribute forces across the vertebrae, muscles, and discs that together support the body. Later chapters of history gradually introduced new environments that changed these patterns. Agricultural work repeated certain movements day after day. Industrial labor sometimes required long hours standing beside machinery or performing precise tasks with the hands. Modern life added extended periods of sitting while reading, writing, or interacting with digital tools. Each transition altered the balance between movement and stillness within the day. Yet the underlying biological structure of the spine remained the same. The vertebrae continued stacking above the pelvis, and gravity continued acting downward through the body. Another quiet change occurred at the same time. Advances in nutrition, sanitation, and medicine allowed increasing numbers of people to live far longer than most individuals in earlier eras. The spine therefore continued performing its role across many additional decades of life. Small structural adjustments within the discs, bones, and ligaments accumulated gradually as the years passed. These changes reflected the long record of movement carried within the body rather than a sudden failure of the spine itself. When these elements are considered together, a clearer perspective begins to form. The human spine operates at the meeting point between ancient design and changing environments. It supports a posture that evolved over millions of years while responding to the habits and technologies of modern societies. The presence of back discomfort in many people therefore reflects a complex history rather than a single cause. It is the outcome of gravity acting on a structure shaped by evolution, movement shaped by culture, and time measured across decades of life. Understanding this perspective invites a quieter way of thinking about the body. The spine is not simply a source of problems to be corrected. It is a structure that has carried humans across landscapes, through changing civilizations, and into the long lifespans of the present world. Its story continues wherever people stand, walk, sit, and move through the environments they create. If the story of the human spine is followed across the full length of human history, it begins to reveal something deeper than a simple explanation for discomfort. The spine is not merely a column of bones supporting the body. It is a structure that carries the legacy of how humans became the kind of creature capable of walking upright across the earth. Long before cities, tools, or written language existed, early human ancestors began shifting their bodies into a vertical posture. This change happened gradually across millions of years. Fossils from ancient hominin species show the pelvis becoming broader, the lower spine curving forward, and the position of the skull balancing more directly above the body. Each of these adjustments helped stabilize the head and torso while walking on two legs. The result was a body capable of moving across long distances while keeping the hands free for other tasks. This transformation played a major role in shaping the human way of life. Upright walking allowed early humans to travel between food sources, carry infants, transport gathered plants, and eventually handle tools that required precise control of the hands. The spine stood at the center of this adaptation. It supported the balance of the entire upper body while muscles and ligaments worked constantly to maintain alignment during movement. Without this vertical column of vertebrae, the distinctive mobility and endurance of humans would not have developed in the same way. Yet the spine that made these abilities possible was never designed from the beginning as a perfectly vertical structure. It evolved from a framework inherited from animals whose bodies extended horizontally. The vertebrae, discs, and ligaments that now support upright posture were originally part of a different mechanical arrangement. Evolution reshaped them gradually, adding curves and strengthening joints to handle the downward pull of gravity. These adjustments worked remarkably well, allowing humans to stand, walk, and run with efficiency. However, the underlying structure still reflects its ancient origins. The spine remains a compromise between the architecture inherited from early vertebrates and the demands of a fully upright body. Through most of human existence, this compromise functioned within environments where movement was constant. Early humans walked across landscapes, climbed, carried resources, and changed posture frequently throughout the day. These patterns allowed different regions of the spine to share the work of supporting the body. Muscles engaged and relaxed as the torso bent or straightened. The vertebral discs experienced alternating cycles of compression and release with each step taken across uneven terrain. Within such environments, the spine operated in the dynamic conditions for which it had gradually adapted. Over time, human societies introduced new ways of living that altered how this ancient structure encountered gravity. Agriculture organized labor around repeated tasks. Industrial production introduced long hours of standing or seated work. Modern life added extended periods spent indoors with relatively little movement compared with earlier eras. None of these changes erased the evolutionary design of the spine, yet they reshaped the context in which it functions each day. The human back now supports a body whose lifestyle often differs from the environments that shaped its earliest adaptations. Seen in this light, the presence of back discomfort in many people becomes part of a larger story rather than an isolated problem. It reflects the meeting point between evolutionary history, cultural change, and the simple fact that the human body continues to live under the constant pull of gravity. The spine carries that history quietly within every movement. Seen across the full span of human existence, the spine can be understood as a quiet companion that has followed the species through every stage of its journey. It stood with the earliest upright walkers who moved slowly across African landscapes millions of years ago. It supported bodies that learned to carry tools, gather food, and protect their young while traveling between distant water sources. It balanced the head as humans began shaping language, cooperation, and memory into the foundations of culture. Throughout each of these stages, the vertebral column remained the central axis around which the human body organized itself. The upright posture that defines humans did not appear suddenly. Fossil evidence suggests that the shift toward bipedal movement occurred gradually across many generations of early hominins. Pelvic bones widened to support internal organs while standing upright. The lower spine developed a gentle inward curve that helped balance the torso above the hips. The position of the skull shifted so that the head could rest more directly above the body rather than projecting forward. These changes worked together to create a posture capable of sustaining long-distance walking. Such endurance allowed humans to explore wide territories and adapt to many environments. Within this evolutionary transformation, the spine became a structure balancing multiple demands. It needed to remain flexible enough for bending, turning, and reaching, yet stable enough to support the body's weight above the pelvis. The vertebrae stacked together like a column of small stones, each separated by discs that absorbed compression while allowing movement. Ligaments bound these bones into a coordinated structure, and muscles along the back and abdomen maintained balance during motion. This complex system allowed humans to walk upright for hours, travel across uneven terrain, and carry objects while keeping the head stable enough to observe the world. For most of human history, the spine functioned within environments that required frequent movement. Early humans walked across grasslands, climbed hillsides, crossed rivers, and rested on the ground. Their posture changed constantly as they responded to terrain, weather, and daily tasks. Bending to gather plants, squatting near fires, lifting stones, or carrying children all shifted the orientation of the spine throughout the day. These variations distributed pressure across different regions of the vertebral column. The muscles supporting the back remained active but rarely held the same position for long periods. In this dynamic context, the spine operated in conditions closely aligned with the evolutionary circumstances that shaped it. As human societies developed agriculture and permanent settlements, daily life began to include more repetitive forms of labor. People bent to cultivate fields, lifted harvests, and processed grain. Later, industrial environments introduced workspaces where individuals stood beside machinery or sat at workstations for extended periods. Modern technological societies have continued this trend, often encouraging long intervals of seated activity while interacting with screens or written materials. Each of these changes has subtly altered how the spine experiences gravity during daily life. Yet even as lifestyles transformed, the basic structure of the spine remained largely unchanged. The vertebrae still support the head and torso above the pelvis. The discs continue to cushion the bones as the body moves. Muscles along the back still stabilize posture with quiet adjustments that occur beneath conscious awareness. The spine therefore represents a meeting point between ancient biological design and the environments humans have created across history. Another important dimension of this story involves the increasing length of human life. In earlier centuries, many individuals did not live long enough to experience the full accumulation of mechanical stress that the spine carries across decades. Today, improvements in nutrition, hygiene, and medicine allow large portions of the global population to reach older ages. The spine therefore continues its work far longer than it once did for many individuals in earlier periods. With each passing decade, small structural adjustments within discs, bones, and ligaments gradually appear as part of the natural aging of the body. These changes reflect the long interaction between gravity and movement, rather than a sudden failure of the spine itself. When these different strands of history are considered together, a clearer picture begins to emerge. The human spine was shaped by evolutionary forces that allowed the species to stand upright and move freely through the world. Cultural developments gradually altered the patterns of movement surrounding that ancient structure. Longer lifespans extended the period during which the spine must perform its task of supporting the body. Within this combination of influences, the experience of back discomfort becomes understandable as part of a long biological narrative rather than a single modern malfunction. The spine remains a remarkable structure that has carried humans across continents through the rise of civilizations and into the present era of long life and complex societies. Every step taken, every posture adopted, and every year lived adds another quiet line to the story written within the bones of the back. If the story of the human spine is allowed to slow down and settle at its end, what remains is not a problem waiting to be fixed, but a quiet reminder of what the human body truly is. The spine is not an isolated structure built for comfort. It is the central pillar of a creature that evolved to move through a restless world. Every vertebra carries the memory of that history. Long before cities, roads, or chairs existed, the ancestors of humans stood upright beneath open skies. Their bodies balanced above two legs while the spine held the head steady enough to watch the horizon. Each step placed the weight of gravity through a column of bones that had once belonged to animals moving horizontally across the earth. Yet this arrangement proved strong enough for a new way of life to emerge. The upright posture allowed humans to walk across continents, transport food and children, and shape tools with careful hands. The spine made these possibilities stable enough to repeat day after day across thousands of generations. Through this long passage of time, the spine was never alone in its work. Muscles surrounding the back adjusted constantly to keep the torso balanced. The pelvis transferred weight into the legs. The discs between vertebrae softened the small impacts created by every step. Together, these structures formed a system designed not for stillness, but for movement. Early human lives reflected that design. Walking across uneven terrain, bending to gather food, crouching near fires, and carrying objects from place to place created a rhythm of motion that changed posture throughout the day. Within that rhythm, the spine rarely remained in a single position for long. Pressure moved from one part of the back to another as the body responded to the environment around it. Later in human history, new environments appeared. Fields organized work around repeated tasks. Factories introduced long hours beside machines. Modern life often places the body in front of desks, vehicles, and screens. None of these changes erased the ancient structure of the spine. They simply created new patterns in which that structure must operate. The human back continues supporting the body within these environments, just as it once supported bodies walking across forests and grasslands. Another change has quietly extended the story even further. Humans now live longer than most individuals did across much of history. The spine therefore carries the weight of gravity for many more decades than it once did. Over such long periods, small adjustments accumulate in the bones, discs, and ligaments of the back. These changes are part of the natural record of a structure that has been working continuously for years under the steady pull of the earth. When viewed from this broader perspective, the experience of back discomfort begins to look less like a failure and more like a sign of how extraordinary the human journey has been. The spine stands at the intersection of evolution, culture, movement, and time. It is the structure that allowed humans to stand upright, to travel, to build, and to grow old within the same body that once took its first steps millions of years ago. Perhaps the most important realization is a simple one. The spine still belongs to a creature built for motion. It responds best when the body continues to move, shift posture, and remain part of the living rhythm of gravity and balance that shaped human evolution. And when we pause to notice the quiet work of the spine beneath us, another question remains gently open. If the human body was shaped for a life of movement beneath the sky, how might it change the way we live when we remember that?